Hey,
Hi, how are you?
good. How are you?
Good, thanks. Just want to make sure you're all set up. You're all okay.
Oh yeah, I'm good.
Okay,
Yeah.
fantastic. Just checking.
Hey.
Maybe the session chat.
Yeah.
Oh, I'm the SB for the session, so
Oh.
if you need any help, just like.
Okay, so you will be outside. Okay. Yeah, thank you. So early. Okay, let's just get started. In this tutorial, we'll be talk about uncertainty quantification and confidence calibration, mostly uncertainty quantification for large language models. These are the co-authors for this survey, and my name is Huawei, the last one here. The other ones are the PhD student. Because of the visa issue, they cannot make it from US to here. And so we have a website, and you can find the slides on there. And you can also find our paper, and we also have a list of papers maintained in the repository as well. So I just pause a little bit for you guys to, if you want to visit the website. You can also find it on the webpage in KDD as well. All right, and so a little bit about me. My name is Huawei. I'm currently an assistant professor in Arizona State University. Before that, I got my PhD in Penn State, and then I go to academia for a while, and then spend 2 years in another university. The overarching goal for my group has always been we want to create autonomous agents which can accomplish tasks in complex physical environments. And in order to do that, we focus on 3 aspects. In order to do it in the physical environment, we deal with real-world data. So that's the reason why we are here in KDD. And then we also spend a lot of more time in making the model trustworthy to operate in the physical environment. And we also try to benchmark and deploy it in the physical world. And so in this talk, you will mostly see the uncertainty part in the trustworthy model, but it's very closely related to the data and benchmarking efforts that we did before. Like I said, the tutorial is also contributed with these 5 PhD students, 3 of them from ASU, the other one is from U Chicago, Chacha, and Chen is from UIUC. And the outline for this tutorial is like this. So we'll briefly spend 10 minutes talking about the motivation for uncertainty quantification and uncertainty quantification in large language models. And then we will try to define some terms and try to understand how the uncertainty and confidence coming from, or why it's different from traditional deep learning models. And then we will spend most of our time talking about the uncertainty quantification methods in large language models. We'll have a coffee break in between, and after that, we will have the second part of UQ methods, and we also will cover a little bit on the confidence, but they are really closely related to the uncertainty in the previous section, so it's going to be very brief. You'll find a lot of contents in common. And then we'll talk about the applications of UQ, why after we have the quantified uncertainty, how can we use that in your either downstream task or in language models? And then we will talk about some remaining open challenges and future directions. And at the end of each section or subsection, I will pause for questions. If you have any questions, feel free to bring it up. And if you want to refer to a certain slide number, it's down here on the right bottom part. Okay, and yeah, so let's firstly talk about why we need uncertainty quantification. So the term uncertainty is not new. It's even deep learning. It's already been a hot topic. So in deep learning, we have a neural network, and instead of just predicting or classifying certain labels, we also want, in traditional deep learning, we also want some distribution of your prediction. We want to know how confident you are in your prediction. One application for the uncertainty quantification in deep learning models is the autonomous driving vehicles. Think about when you are given this image. One task in autonomous driving is you try to predict how the depth of the objects to your observation point, right? And this one is the predicted depth. And usually people, when you predict the depth, you also want to estimate the confidence of your predicted depth. So each pixel will be given, instead of just one label, it will also given one scalar value indicating the confidence of this prediction. So this one here, they're using entropy, and with this confidence, and they can help the downstream tasks like should I steer my such steering left or steering right. If I'm not confident enough, maybe they'll be taken over by some other more trustworthy models, like human expert models. Okay. And this is just traditional uncertainty in deep learning. And then with the growth of language models, we see that it's more than just one or a few layers of the network. The model is getting bigger and bigger. And people have a natural question like, as the model grew bigger, and does their uncertainty also grow, like their estimation of the uncertainty, is it becoming better? And then people conducted an experiment. So they're finding that our large language models, they exhibit overconfidence, which means that their confidence scores is higher than the true likelihood of the correctness. So in this figure here, you will see the poem, this language model, consistently exhibit overconfidence. With x-axis is the confidence and y-axis is the accuracy. So the x-axis are like are binned into several intervals that they try to do an statistic analysis on how much how much of the samples their prediction confidence lies within this interval, and how much of the portion of the samples lies within this area. So the dashed area here is perfect. If you have a perfect sample, a perfect model, and its confidence scores is matching his true likelihood of correctness, then it's going to be this perfectly dashed area. But if it's smaller, the blue is the actual distribution of the samples predicted and the confidence and the accuracy. And then it's meaning that your predicted confidence is actually higher than the accuracy you're achieving, which means you're basically overconfident in your prediction. And they conduct the evaluations on 4 models. Llama 3 8B and Llama QN 2.5, DeepSeek, and E. All of the models are exhibiting the overconfidence issue. So then this brings the next question is like, if the models, language models, they are getting bigger, but they're not getting like more like trustworthy, and how can we trust the models? And that's why the uncertainty quantification lies in. So think about the most knowledgeable person you know, like maybe a professor, a colleague, or even a close friend. I think when even they will make, sometimes they will say like, I'm not sure about that, or it's outside my area of expertise. But right now, the LM suffer from this kind of overconfidence issue. And this is when they confidently, which means they confidently generate fake answers, or they make things up, or even when they actually don't know about the correct information. And so this is a serious problem. And let's look at a few examples here. So here we have this ChatGPT online version, and you can also see that they are explicitly saying that they can make mistakes. And you need to check the important info. And then on the right-hand side is also like the language models are generating something that is not matching the actual knowledge. And this example basically shows why understanding this confidence or understand their uncertainty is very important, because we want to know when the language model is confidently wrong or absolutely critical. And another example here is like if you have this uncertainty, and then we can let the users know, and they can like trust the model. But sometimes the uncertainty quantification is not a easy task for language model. And you can take a look at this example here, and there's a risk prediction model. It tells a user you are very likely to have a heart disease, and in the next 10 years. But even it gave it an accuracy score of 0.85, and it provides some model reasoning based on the factors like age, cholesterol, and daily alcohol consumption. But then the user might have follow-up questions like, how reliable is this actually? And can I really trust this model with this serious prediction? And how about like my BMI? How about my my family history? The model might not have consider these factors, but they simply do not have such information. So this is exactly where the uncertainty become invaluable. If you have a model saying that even though I gave you a prediction, I have certain uncertainty that's pretty high, but you give me more information, the uncertainty continues lower. It can gain some the trust from the users, right? And then another example here, we can think of question answering or reasoning as a process of information seeking. Like I said, if I'm giving you more information, then you are the language model as an information seeker. They can gradually ask more questions if they're not confident, and if they know what question to ask, then they can gradually improve their confidence in their prediction, and the users will also try to trust this model as well. All right. And that's basically why we need uncertainty quantification, because the main thing here is we want some reliable response to gain the trust from the user. And I'll pause a little bit here for section 1. If you have any questions, feel free to bring that up. Yeah.
Do you find it useful to give a confidence as a range? So that way, early on in the questioning, if the range is wider, and then the users provide more information, they can see the confidence range get narrower, that reflects more confidence.
Yeah, so I think if you have a range, like say between 0 and 1, then the user can know like, is it like really high confidence or low confidence? And I think if you keep interacting with the users, the trend for the confidence will be helpful more than just a number. And but right now, like we'll see later, if you are calculating entropy, it's highly likely it's not between a range of 0 and 1. So there are some confidence measures that propose between a certain scalar value, but most of them are not like bounded values.
I mean, empirically, if you're validating, you have labeled data, then you can validate
Yeah,
to get the probability of it.
yeah, you can calibrate that. Yeah, yeah,
0 to 1.
yeah.
But I guess my question of feedback is, you give users a feedback and the user sees the confidence percentages between 65 and 85. They give some more input. They see it's between 67 and 69. Then the 67 and 69, that range being much smaller.
Yeah.
Just like when you do a time series.
Yeah.
You have a confidence interval. The farther out you go.
Yeah. So I think like this, like I said, the users might want to see the trend other than just a single value. But yeah. When you provide more information. Yeah.
I'm just curious, like in terms of just so we have a shared vocabulary, I've seen like all sorts of ways people calculate confidence. I'm curious, like when we're talking about confidence in this aspect here with LLM, what way are we talking about it?
Yeah, I will talk about it in the next section. I will try to define the terms. Yeah.
Do you also have an issue of severity that's independent of confidence? Like I'm confident you have a cold 90%, but the severity of a cold could be 10% severity. I'm confident you're going to die in 2 days. The confidence could be 10%.
Yeah.
The severity could be 90%.
Yeah, I think it's depending on, we'll talk about later, like when people talk about like confidence or uncertainty, what aspect of uncertainty are talking about? Is this data uncertainty or model uncertainty? We'll talk about later.
Same thing comes up with financial risk.
Yeah.
Because the severity could be proportional to the dollar amount.
Yeah. All right, so I think that's it for the section 1, and then the section 2, we will finally like define the terms, what we are talking about when we're talking about the uncertainty and the confidence, right? So first, let's talk about the traditional way of people thinking about like the uncertainty. So they will always think about the aleatoric and epistemic uncertainty. So if you're not familiar with uncertainty, this will be a very quick introduction on how people view uncertainty in deep learning or in traditional machine learning. So first aspect of uncertainty is called data uncertainty. This is how like people view the uncertainty of a prediction coming from. So one part of the uncertainty coming from the data or aleatoric uncertainty. So think of this as inherent and irreducible randomness or variability that is simply like present in the data. And no matter, and it's called the data uncertainty actually. And the key here is no matter how much data you collect, or how perfect your model is, you actually cannot really get rid of this type of uncertainty because it's a part of the world, because it's not a flaw in your model knowledge. It's just the data, the real world data is messy. And think about this down below example here. This red dots are the real world data. They themselves, like the x-axis is a feature, there's one-dimensional feature, y-axis is a label. Then you can see that the mapping from the same value in the feature corresponds to multiple values. So even though you have a perfect model, your data is very noisy, and this range here, it given me one input of the features and the prediction, like variances in your model will be, or in your data, would be considered as aleatoric uncertainty. And another example here, so you have this x-axis as the features, y-axis as the label, and you have two groups of data, and you can see that this data is more messier or noisier than this kind of data. So then people think of, okay, I'm thinking this part is having high aleatoric uncertainty or data uncertainty, and this part having the low aleatoric uncertainty. And comparing to this data uncertainty or aleatoric uncertainty, there is another type of uncertainty in traditional uncertainty perspective on deep learning models, which is called epistemic uncertainty. So it comes from a lack of knowledge on the part of the model itself. So they could be due to its model's architecture, or more commonly, it's the model just haven't seen enough or diverse representative training data. So that's the reason why it's also called model uncertainty. So unlike data uncertainty, those epistemic or model uncertainty, they can be reduced. So think about Here in this area, they are having this, the model have never seen this data before, so they will have a high model uncertainty or epistemic uncertainty. So if you have more data, collect more data in this part, then your model's like epistemic uncertainty will reduce. And in this example here down on the right is just showing the difference between aleatoric and epistemic uncertainty. So think about if you do not have the data on this part, and then even if your model can make predictions on this part, and even if they are facing the same training data, they could have different predictions or mean predictions on this area. Say I train 3 models and their prediction, they're perfectly aligned under this range when your data covers it. But when it's out of the data coverage, then your 3 models could predict like 3 curves here. And the variance of these 3 curves going to be considered as epistemic uncertainty or model uncertainty, right? And then people think of this view. Think about like when your model trying to make a prediction from the probabilistic perspective, the variance. If you think about this model, like you have a input of features and output a mean and a variance. So when you make prediction, you will use the mean, probably using the mean as the predicted value, or you sample one value out of this normal distribution. And then people think of data uncertainty as the expected value of this sigma square. And then the model uncertainty is the variance of mu. Think about this one, like we are having this dashed orange line is 1 mu, and you have 3 mu's. You are trying to calculate the epistemic or model uncertainty as the variance of the mu. And the data uncertainty is just the expected variance of the sigma square when your model make predictions, right? So even you have the same data set as that, even you have the same data set, you still can have like variance model parameters learned from the same data set, so that when you're making like your variance on the uncovered area could be very different. That is how people measure the model uncertainty, right? Any questions here about the data uncertainty and model uncertainty? All right, and that's the basic view of traditional uncertainty in deep learning models or in machine learning models. And then let's think about how the language models are different from the traditional like predictions or uncertainty quantification for the prediction on the deep learning models. The first thing is it has a lot of parameters. That's the reason why they call large language models. And when you have a large amount of parameters, and then your estimation for the uncertainty becomes costly. And one traditional way of estimating uncertainty is doing ensemble. You train multiple models, and in order to calculate their data uncertainty, you have to have multiple models, and you calculate the variance of their mu, right? And then that is how traditional way of uncertainty quantification estimating the uncertainty with ensemble methods, but with a lot of large number of parameters, you might think like doing this is infeasible, right? And this is like the challenge on the scale of the model. That's one challenge. Another challenge is the input ambiguity on the language itself. So this is, think about language itself has ambiguity in its input. Even though we have exact words, their embeddings could have ambiguity based on the different context. And if sometimes people are describing their need in unclear prompts or incomplete prompts, and they have to clarify that with multiple interactions, and the same sentence could have like multiple interpretations. Say in this example here, when the user asks when did Harry Potter this movie came out, and seemingly it's a simple question. But if you look at the Wikipedia source, and you will find this premiered in London on November 4th, 2001. And then, but it's actually released to the cinemas in the US and UK on November 16th, 2001. So the model might respond with either date, both being technically correct and being on the implicit meaning of came out. And how do we actually interpret this certainty when the model itself has inherent, or the input itself has inherent ambiguity? So this type of challenge also makes us think, is this uncertainty more like aleatoric uncertainty or the model uncertainty or data uncertainty? Is it because the input data or it's just model do not know? It's really hard to quantify whether the model really don't know or the data itself has problems. And if you view that as a aleatoric uncertainty, and because the input data has inherent variability, then you can do some clarification to make sure the data has like input data is more clarified. But if you consider it as an epistemic uncertainty, and the model might not have enough knowledge, like my model have not been trained on those kind of data and is not well trained, and then what should I see this uncertainty coming from? So that's a gray area, like where the longer models usually frequently encounter in the real world interactions when you are inputting a ambiguous language. And then another challenge for longer models is the decoding stochasticity. Let's think about like most of the longer models, they are autoregressive. So you have traditional models, you just have one output, the classifier, you have the probability on the final, categories, the probability on each category. And but if you have longer model, it's gonna be different. So you can see the input here as an initial input, and your model may give you an token probability. And then this token probability will be taken later into the model's input as well. So you can think of like the uncertainty in the beginning, they may propagate from one token to another. And so here in the very first token, it consider panda with 0.7 probability, and then with 0.2, with 0.1, so then picks the panda, and that chosen word, like I said, is going to be becoming part of the input. And then this inherent randomness or stochasticity in the decoding process will be a major challenge for autoregressive models when you're making predictions. And then another different challenge here is like you have different ways to get to one final answer. Even though my input is very clear and my output for one value might be, I also have like one specific output, like the ground truth answer, but the way we think about, the way we get to that answer could be different. Think about like when you try to solve a math problem, like different students might have different solving strategy. So that kind of divergence in the actual reasoning path could also lead to the divergence in or uncertainty in your long-term model as well. So depending on which path a model actually effectively takes, even for the same input, like I said, it might arrive slightly different outputs and even to different final answers, at least in different levels of the confidence. So this inherent divergence in the internal reasoning process of a language model or your question makes things much harder to pinpoint whether it's one single source of uncertainty or which uncertainty contributes most to the final answer. So that's another challenge for a language model as well. Okay, so we've spoken enough about like uncertainty, and then let's talk about the terms. Right, so in the uncertainty in the language model context, it's mainly is a uncertainty response to one certain input. Right, so the X is the user input, a fixed given user input, and it's also the uncertainty in the in this context would be usually the variability of all the possible predictions of a language model given a fixed input. So it's it's conditioning on the input, definitely. It's also sometimes conditioning on the model itself as well. So, but mostly people think of this uncertainty in longer model context is I'm quantifying uncertainty for this model given this input X. And if you write it out, it's like this one here is a entropy. H is the entropy. Then you can use this equation here. It's saying I'm quantifying given this input and all the generated outputs. I'm quantifying their entropy. Right, and then when we talk about confidence in later part of this tutorial, we're talking about the confidence of the model generating given one certain input and an output, the probability of generating this inputs, this output given the input. So it's basically the probability of given this input X of generating the output S, right? Okay, so the uncertainty is like spread all of the possibilities on all the possible generations, but the confidence is just talking about one single belief in the specific generation, right? So hope that clears things up. Like that's very like uncertainty talking about all the possible outputs, and confidence, we're just quantifying one output. And later, when we talk about the uncertainty quantification methods, we also usually like people consider different settings, right? So if you have the model's access to you have the access to the model's output probability or the model weight, then we'll consider it as a white box. So also sometimes people like when they said the gray box as setting is like they only have the outputted probability of certain tokens, but not the whole model. But we also consider that as white box because they have the model's probability on certain internal parameters or in the intermediate results. And in the black box setting, we do not assume like we have the probability distribution on certain logics. We only have the generated sequences or generated token, right? And this is less constraints on the models. Normally it's sampling multiple same question with multiple times and uses their consistency as uncertainty. But for this equation here, if you are calculating this distribution, then usually you will have the SI is certain token, the probability of certain token. If you are having this access to the probabilities, you want to estimate the probability of generating a sequence given a input, then people will consider as a joint probability given by the every token, the probability of every token generated, right? All right, and this is just an example. Like I said, the uncertainty measure is a property of the perceived predictive prediction given one input X. And it's considered the dispersion or variance of the predictive distribution. Say here, this question, given this question, where could you find only a few of it? Then the model is outputting those kind of output like in a small town or village, in an empty building or basement or a library or museum. And you can see that this variability on these answers will be like a pretty diverse, right? And then if you have a different question where you would find magazines alongside many other printed books, a lot of the answer is going to be like bookstore, library, and in the library, then then the distribution expected would be something like this. The answer, the distribution for this question would be more dense, right? And then the distribution for the blue, the question one would be something like blue is more spread out, right? And then when we talk about the confidence, so in the previous one, like we actually people are, if you're using entropy, they're gonna calculate it in this way. This first one is much higher than the second one, the uncertainty. But if you're quantifying confidence, is depending on both, like I said, both on the predictive distribution and the answer itself as well. So we can think of it as actually looking at this graph on the right. The peak represents the most likely answer, and the high confidence would typically be associated with the very top of that peak, and low confidence would be further down the slope. And the probability for choosing that answer with a low confidence would be isn't that strong. So even if you have like technically most likely, but it's also like the confidence is not high because this question itself has a diverse or flat distribution. Right. We have the overlap issue here, but basically, many like the confidence estimation is highly overlapped with uncertainty as well. So they have many shared algorithms between confidence and uncertainty quantification. A lot of the algorithms can be used in both uncertainty and confidence estimation. So one way of doing that is if you have a estimation on the confidence of each generation. This is access overlap. If you have the uncertainty, the confidence for each estimated generated output, then one way of defining the uncertainty for that answer or for that input is just taking the maximum and then take the negative value of that input, because it implies if you have a very confidence high prediction and in your model, your uncertainty is very low. And so there are often two sides of the same coin, focusing on slightly different aspects of the model's output, but they are closely related as well, right? And then after we talk about the definitions of uncertainty and confidence, let's talk about how people usually evaluate. So unlike the classification or regression tasks, you have specific labels. And uncertainty confidence, sometimes we don't have that label for the confidence, but how people evaluate the uncertainty. And there are two matrices, two kind of matrices, like the area under ROC or ARC, or the calibration matrix like expected calibrated error. So I'll explain one by one. So an expected uncertainty score could be intuitively should be able to predict whether a generated answer is correct or incorrect, right? If you have a very high uncertainty and it's highly expected that your model's prediction gonna be incorrect. And then people are using this matrix readily used. Basically, every paper will cover that. Is AUROC. It stands for the area under the receiver operating characteristics curve. To understand this curve this curve here, and we often start by thinking about a confusion matrix. It's simple but powerful. It's a simple table here, and help us to visualize the performance of the prediction problem. So it breaks down outcomes into things like true positives, like I'm predicting a positive label and it's actually positive. And false positive is often wrongly saying an answer is correct, but it's not. And true negatives and false negatives is a similar definition. And from the confusion matrix, then we have this, we can plot an ROC curve. So the x-axis is going to be the false positive rate, and the y-axis is going to be the true positive rate. And ideally, we would want a high FPR for positive rate, meaning we are not incorrectly flagging too many things. And a perfect classifier would be the top left corner, and as the blue line getting closer. And a random classifier would just follow the dotted line. So you're having 0.5 all the time. And the AUROC score itself is simply the total area, like the area under the curve, the blue line area under the curve, and the green line under the curve. And the higher AUROC, if it's closer to the upper left point is going to be 1. It means like your uncertainty score is doing a great job at distinguishing between correct and incorrect answers. Sometimes we, like I said, even though we don't know the confidence of certain answer, but we still know the golden answer, right? So if you have a golden answer, and think about like the multi-choice classification problem, like multi-choice problem when you are given one question and you want the language models to choose from this 4 or 5 answers. And that is like we call it a classification type task. And you can just simply matching whether the model's output matching with the ground truth label, like you have a golden answer. And then for the generation tab task, like we need to decide whether a generated answer is correct or not with an additional step, which like comparing the semantic meanings between your generated answer to the golden answer. So with that golden answer, like I said, you can decide whether its generated answer is correct or incorrect. And with this correct or incorrectness, then you can calculate this true positive rate and false positive rate and get this AOROC curve, right? And that is one metric, like AUROC, but people are also using like confidence calibration based matrices. So the intuition is like if it's a well-calibrated model, then for any prediction, its confidence should be equal to its accuracy if you have multiple samples in the distribution should be following their confidence and between their confidence and accuracy. And then the calibration metrics is there are 2 widely used calibration metrics. One is the ECE, the expected calibration error. And then the other one is the Bayer score. So the ECE is probably the most popular one used in the current language model uncertainty quantification methods. And it works by like grouping the prediction, like I showed before, you have multiple beans, grouping your predictions based on their confidence. And for example, if all your predictions, for all the predictions where the model has a between 0 and 10% of confidence and 10 to 20 confidence and 20 to 30% of confidence, like you can group your predictions, fit that prediction into certain bin of confidence distribution. And for each bin, it measures the absolute difference between the average accuracy or predictions in that bin and the average confidence of those bins. Say if you're measuring a average confidence for the bin between 50% to 60%, then the mean, the average confidence would be like 55%. And then you will calculate an average accuracy based on all the samples or the prediction fixed into that bin. And then you get a average accuracy, and you want to make sure that this average accuracy within that bin and it matches the average with confidence within that bin as well. And then you calculate through all the bins you have, right? So that's the expected calibration error. And then the Bayer score is another metric. It measures the mean square difference between the predicted probabilities and actual outcomes. So if the outcome is 0 for incorrect and 1 for the correct ones for these actual outcomes, and it penalizes both miscalibration. So miscalibration means like when the model is its confidence does not match its accuracy, or its poor discrimination. It means like if the model does not tell correct from incorrect well. So a lower Bayer score here means it indicates better, like better overall performance or calibration. And both ECE and calibration and Bayer score, they're super helpful in calibrating the model's confidence. And sometimes people are also using this ECE or Bayer score in their loss function if you're doing supervised learning. So if you want to train your model to output confidence, and then this ECE or Bayer score, they could be used as a supervised supervision for your model's output. You have like I said, is extra output for your model. The extra output is going to be the confidence. And let's just do a quick example, a concrete example here. Say the model's confidence, it has like 10 data samples. And then the model's confidence for each prediction is the first column. And then the second column is whether this prediction is correct or not. So the prediction is going to be something like this. It's generated text. Like I said, it's in a library in a small town. And then the ground truth text for this question could be in a library. And the ground truth for this second question could be in a small town. You have multiple data samples, like could be different questions, and so that they could have different ground truth answers. And then you will compare the generated text to see if that is correctly predicting the ground truth. Like I said, if it's a text, then sometimes you will have additional step by comparing their semantic meanings, decide whether your prediction is actually correct or not. And then if you're calculating for ECE, and then you will do this bin, like I will bin the confidence intervals into between 0 and 2, 0 and 0.2, 0.2 to 0.4, then from 0.8 to 1. And then I count how many samples falls into this bin, and then get their average confidence. Then for example, in this bin, like 0.2 to 0.4, I have this 3 data samples here, right? And then this average confidence for this 3 data sample is average of this 3 values is 0.3. And then the average accuracy, I think it's something. Oh, okay. So I think it's something wrong. Okay. So those two, they are falls into 0.2 to 0.4 bin, right? So and their mean of their confidence is 0.3, and these two samples are then calculated with this equation where you averaged over like the overall number of samples. Here you have 2 samples falls into this category, and then overall you have 10 samples, and you have the mean confidence of this this sample. And like I said, the accuracy for them is 0, and you are doing the absolute value. Then this is a first term here. That's how you actually calculate a ECE value. Okay, and that's basically conclude the second section. We understand or we define the terms for uncertainty quantification confidence, and we also understand how we evaluate the uncertainty. Basically, if you have a golden answer, then you can evaluate it. Right? Okay, question.
On your slide, defining the terms, when I use the LLM temperature as a prior, or you could do some empirical tests.
Oh, so you said whether you should use temperature.
Yeah, the LLM temperature, because for some things and also one dimension be temperature, another dimension be context. Like if you're in the vault of tree search, and you're exploring a lot of alternatives with a high creative temperature, may not necessarily be detrimental.
Yeah, so that's actually you're getting ahead of me. Like there's one way of quantifying uncertainty is changing the temperature and getting multiple outputs, and then you're quantifying the divergency of this outputs. Yeah, there is one specific method later talking about that. Yeah. Any other questions for section 2?
I have
Yeah.
I think this might be something I'm probably gonna cover later on anyway, but I was curious, like, with the confidence values that you showed in just like through the slide. I know those are like examples, but if you were to do this for an LLM, are those like just output by the LLM, hey, what your confidence value you think it is, or it's more like you go by some other methods to calculate those?
So your question is, you will just quantify the uncertainty by the output of the LLMs, or you will go into the model parameter itself?
Yeah, so is this the output tokens that you're using to quantify the confidence, or is it more like?
Yeah, we'll cover it later. Say, like we said here, the definitions of uncertainty and confidence. So you want to quantify the generated output sequence, right? So there's multiple ways to estimate that. The sequence itself, if you know the probability, you can calculate the distribution of the probability, joint distribution of the probability of the tokens. And sometimes people do not do multiple sampling. They are just using one generated, joint probability from one sequence and treating that as uncertainty. And if you're then usually like I said, like the confidence are actually based on certain outputs, right? One output. So if you have the probability for certain tokens in the sequence, then usually you're doing confidence. But like I said, sometimes people if they do not generate multiple times, then they'll use that confidence as uncertainty. And of course, if you have access to the model itself, then you can get the probability for each token. But if you do not have access to that, you will just do multicolor sampling or sample multiple times and estimate this joint probability. Yeah.
I'm thinking like what is it that is more closer to like this sort of definition? Is it like doing a Monte Carlo sampling or just looking at it?
Yeah, I will talk about I think you guys are super smart. We already talk about the very basic or very early explorations for uncertainty quantification. So like I said, you can when large number models coming out and when you try to quantify the uncertainty or confidence for a generated sequence, then those three are the things that people usually think about, right? So the entropy or aggregated probability on the tokens could be one. So let's think about the entropy. It's a general term in physics, but basically it's borrowed by the computer scientists. And it indicates like if you have a higher entropy, and then it basically tells you like your higher uncertainty. So it's a measure of randomness in the probability distribution and quantifying how unpredictable the model's prediction for a given input. So you can calculate the entropy for the sentences, right? And then if you're calculating for sentences, and then this T is like for a specific sentence, and then you have certain probability for a sentence, and then you just calculate the probability, the entropy for that sentence. And this probability for a certain sentence, it could be, if you have, like I said, for any probability, you can estimate it through Monte Carlo sampling, or you can, if you have the model's output probability for certain token, then there's joint distribution for every tokens for that sentence, right? And this is a sentence level entropy. And you can also do a token level entropy. It's basically measuring how likely a language model assign each individual token in a sequence. Then when you consider for the sentence level, the generated sequence level uncertainty, just use a maximum of that entropy for each token, right? So that's the entropy definition. It's a very early work here. They're trying to estimate generate the uncertainty for a certain generated sequence from language models. If you have, like I said, if you have the model access to the models, and then the probability for each token going to be used here. And then if you want to, you have the entropy for each token, then you will, like this paper, they define the maximum of that entropy as the entropy for the sentence. And then if you have if you want to use the sentence level entropy, then just do the joint distribution, joint entropy for every token, right? And then there are some other ways of aggregating probability, right? If you have the probability for a certain token, there are multiple ways to aggregate it. You don't need to have to do entropy. You can do maximum entropy, like I said before, and you can also do minimum entropy, average entropy, and the standard deviation of the entropy between the tokens. And also you can do the likelihood. You do not need to do entropy because entropy is defined P log P, and then you don't need to do P log P. You can just do the likelihood directly. And there are multiple ways to do that, and like you can have multiple ways, but there is no like clear winner for different data sets and different tasks. But it's a very intuitive way of estimating entropy, the probability.
So I may be misunderstanding this, but I think given the stochastic nature of the output coming out of an LLM, there's a reliance on semantic similarity to establish confidence. However, for very short things, it works short. It's going to work well. But if you're getting LLMs to produce large amounts of text, that's like in the end, the semantic similarity distribution are going to look almost the same all the time.
Yeah. So I mean, you are getting ahead of me. Like this is very simple, basic one. Like then people starting to find out like not every token should be treated equally. They should have the different weights for a certain token.
The reason I went there today to find uncertainty, increased context. We put more text in there, right?
Yeah.
Putting more text in there, I'm already now struggling against the concept of how I'm going to measure this.
Yeah. So like I said, if you're putting if you are having certain weight on every on certain token you generated, then that could be solving the problem, because if you are generating more and then those weights for those tokens are not important, and then like your entropy will not change.
Would need to learn those tokens from.
Those
tokens are important for that specific.
Yeah, I mean, like if you're doing a supervised learning way, if you want to calibrate so we're just now doing quantification. We do not change the model yet. So if you're just doing the quantification, you do not change the distribution. Hope that clears. Yeah. All right, so that's one way of if you have the probability and then you want to aggregate it, entropy or those kind of massive ways of aggregating probability could be your choice. And then another straightforward way of estimating uncertainty is like deep ensemble, like I showed before. Like traditionally, people have like deep ensembles, and then they treat those data uncertainty and the model uncertainty like differentiated easily, and then the sum of them would be considered as total uncertainty. But it's really hard or training separate models is going to be impossible for one language model when you're trying to generate the uncertainty for one model or for given a input is probably impossible, and or it's computationally expensive, I would say. And then, like I said, you can change your base model like into multiple versions, like by tuning the temperature, and you can generate multiple outputs. You still based on the outputs distribution of the outputs to get the distribution, and then estimating their variance. And but usually people do not change the model internal ways. They're just changing the last layers or modifying certain inputs like context for the model and get the different outputs. But deep ensembles is a big general idea for estimating uncertainty. You can use that as well if you're able to afford those computational resources. And another way, a very easy one, and like it's surprisingly like working in certain cases, is like just ask the language model itself. Like say giving you, there are two kind of methods. Like one is P2, like I'm just given this prompt to the language model. I have a question, I have an answer, and I have I also ask the language model, say the probability of then for the language model to give me a prediction on whether it's it's A or B, and I just use the probability distribution for A and B from that language model as the evaluated confidence. That's the self-evaluation. And also, you can sample the question. If you do not have the outputted probability for the language model, you can just ask multiple times and just estimate the probability. And that's the general way of people like doing asking language model to self-evaluate their confidence. Or you can just ask the language model. There are multiple ways you can. I think there's also like this way, like it's called self-probing, where they ask the language model to when they output an answer, they also output a probability or confidence directly on that output, right? So that's a very easy way to do that, right? And then like people show that like with the increase of the model size and these self-evaluation is getting better and better. Like people are still investigating why this is the truth, but this is what they find. Like as the model size grows, your self-evaluation of that answer tends to grow, like the AUROC or ECE tends to perform better. Right? And that's all. I think that also makes sense because like as the model size increases, you have the model that's more generalized to out of distribution samples, and then you're estimating the probabilities better, I guess. But there's no like clear conclusion for that observation. All right, so right now we have talked about, we already touched on the section 3, like the uncertainty quantification methods. We talk about the very early explorations. You can do like aggregated probabilities if you have access to that. And you can also do some variances of deep ensemble. And you can also do self-evaluation, ask a language model itself to output a probability or do it multiple times, generate the output probability. And then let's talk about some like more complicated techniques that sort of based on the similar idea, but it's dealing with certain specific challenges, right? And corresponding to the challenges from like previously we talked about the challenges of large language models in estimating uncertainty. Then there are different categories of the uncertainty quantification methods for different mechanisms. So the first category we're going to cover is the input uncertainty, where people just manipulating the inputs or the context to the model so that they can, when they get outputs, they can get different outputs, and then they calculate the differences between the divergence between the outputs. So the definition of the input uncertainty is like basically they're saying the uncertainty coming from the model, model input itself. So when the input is ambiguous, vague, or underspecified, and the model, like this kind of uncertainty is much higher. Expected to be higher. And so here is the example. If you ask what is the capital of this country, and without any context, and which country, and then this input uncertainty could be very high. You are expecting this input uncertainty could be very high. And another example, like when you prompt the model to summarize the document, it might yield different responses depending on the expected level of detail or focus you want your language model to do. And like my personal like thinking is like if your input is ambiguous, it should be considered the aleatoric uncertainty. So it is inherent randomness because your input variability. But I'm still debating with my students because sometimes they said this model is too weak to conduct this task, and your task is too complicated, and this should be considered as a model uncertainty. But like this like back and forth argument on this certain uncertainty, whether it should be down to aleatoric or should belong to epistemic, is continually going up because language models is so complicated. You have no idea like what this certain kind of model has been used certain data or not, right? All right, so let's talk about specific methods in the input uncertainty. The first kind of method, we'll cover 3. The first kind of method is the input perturbation sampling. The idea is very simple. So in this paper, they claim they address both epistemic and aleatoric uncertainties. So the aggregation, their aggregation yields the total uncertainty. And so this is a motivating example from the strategy QA dataset. So basically the idea is like if you have a certain input and you have the certain temperature as default, and you have the perturbation module, that perturbation module is going to perturbate on the temperature and perturbate on the input as well. So you will generate multiple inputs, and you will also generate under certain temperature. And then with each of the combinations of the perturbation, then you will have the output, and then you will have the aggregation module. And here, the aggregation module is using this term. It's the S, yi and yj is simply the similarity between the generated output, the similarities between them. And then this weight here is the similarity between the input x0, the original input, and the perturbated input. And if the idea is like if your perturbation is more similar and is prioritize the milder perturbations over extreme ones. If you have like a very different similarities for this after perturbation, then it's likely your generated sequences between and their similarities could be very different from the original one. So you want to penalize that very different different context input. But they do not have like the control on the perturbation, whether it's semantic or not. They just use stuff like the dummy tokens. I think in their paper, the dummy tokens are the most powerful one. And they can also do paraphrasing, that's sort of semantic. And they also do the some system messages, like they have insert certain fixed input into the after the original input, right? And if you can think of like if the SI and SYI and YJ is do exact matching function, you do not compare their semantic similarities, it's just do exact matching, then it's basically the value of 0 and 1s. And if your weight is 1, you're just basically doing the majority voting, right? So you put the weight over every output equally, and then you just do exact matching, and then that is just majority voting. And this is their results. So they conducted on two kind of types of data sets. One is the classification type, like they have provided the choices to the model, and the model have to make choices between these 3 or 4 choices. And then this generation type data set is just open text as generation. Then they have when they do the evaluation, they have to compare the similarities between the generated sequence and the output sequence. And they also do a the ablation study or sensitivity study. They try to perturbate the temperature, and they also do the investigation on different perturbation strategies or aggregation strategies. And then you can find out like I think these they do not really have much difference. But if you increase your perturbation, it definitely makes your ECE much higher. Your estimation for the uncertainty quantification is much better, because you want your generation to be diverse or covering the output distribution, not just condensed into certain fixed input. If all the input is fixed, it's not helping you do the quantification on the uncertainty, right? And then the second method is called input clarification ensembles. It's sort of like it's also doing perturbation in the input as well, but it's just adding some clarification on the input, because like I said before, the input uncertainty maybe is people are believing that input uncertainty coming from the input itself. Your input is ambiguous. So that's the reason why they want to generate some clarification for the input, so that it's getting clearer. And then the steps for this method is, I think the labels are wrong, but the first step is generating the clarification set. They are using another language model, like clarification language model, to produce multiple phrasings or clarifying statements for an ambiguous input. And then they form this input with a new clarification together, concatenate together, and feed that into the language model to sample the new predictions. And then in total, you will have if you sample it t times and you have k clarification clarification text for each input, then you will have k times 10 final sampled output answers. And then another thing they do is to do semantic clustering. They use another LM to cluster the semantically equivalent answers into unique labels. And then the reason why they are doing this one is because these samples are too many, and sometimes they are very similar to each other. So they want to generate clusters and compare and just calculate this variance between clusters other than between each generated samples. And this reduces overestimation of entropy. And then the next step is to compute the total uncertainty. So there's the entropy before clarification. And then they compute the epistemic uncertainty. It captures the expected average entropy of the model's prediction across the clarified inputs. So total uncertainty is before the clarification, and the epistemic uncertainty, they are treating it as after the clarification, with clarification. Right? So we're just using an example here. So the input is who is the president of this country, and your clarification set, if you set it to 3, and then for the first set, you will have one answer like assume this the clarification could be assume this country is United States. The second is assume this country is France. And then the third one is which country is being referred to. And it's just very ambiguous and without clarification. And then there's for each after this clarification, and then you concatenate it with the original question, and then you get the answers. So for this set, for this clarification set, and you will have 10 output answers like Joe Biden for the United States. And then for France, you will have like Macron. And then the third one, if it's the unknown, then it generates it's generating the Germany's presidents. 6 of them are I don't know how to pronounce this, Frank, and the other one is Olive. And then this one is going to be the semantic model predictions. And then you do some clustering. So after clustering, you will have these 4 clusters: Joe Biden, Macron, Steinmeier, and the Scholz. Then you calculate the total uncertainty based on this clusters. Right, so this is before, it's sort of like before the clarification. And then you calculate the epistemic uncertainty. You are calculating the entropy within that cluster. So for the first clarification set, then it's very dense. All of them are Joe Biden. And then for the second one, all of them is Macron. And for the third one, it's a little bit diverse and has certain entropy larger than 0. And then this expected entropy going to be something like this, right? So you can see that the total entropy is calculating among all the generated clusters, but this epistemic uncertainty just calculating within this cluster and calculate the mean of it. Right? So that's their way of modeling the uncertainty and viewing the epistemic and total uncertainty. And then when they try to calculate the aleatoric uncertainty, they just use total to minus this epistemic uncertainty. Right? And this is their results. So the table 1 focuses on the uncertainty quantification for mistake detection. So this means if like how good is the method at telling us the different LM's answer is actually wrong. And they're looking at the factual QA and the GSM-8K for the factual QA is natural questions, like natural language questions. And then this GSM-8K is a math reasoning task. And this paper method shows higher AUROC and F1 scores compared to the other baseline method. And then table 2 is showing the ambiguity detection. So this is where the input is the input clarification ensembles actually addresses, because it clarifies whether certain inputs is ambiguous or not. And again, you can see their method is it's demonstrating superior experience than other baseline methods. So this results is basically highlighting that the input clarification ensembles is really good at detecting general mistakes, but is particularly powerful at distinguishing why the model is uncertain. So whether it's due to the input ambiguity or something else. Okay. And the last category for the input uncertainty methods is the few shot demonstration sampling. Like I said, the input to your models could be different. It could be clarification. It could also be some demonstration text or in context samples. So that's how this paper is doing. So you can think of the other parts are all similar. They're all similar to the previous paper, and they just change the input. The input is not a clarification. It's a sampled data from the training data set, right? So the training data set could be a randomly sampled, or it could be sampled from the similarity-based answers, the similarity-based questions. And then they have two kind of strategies they explored. So the random one, you can see for every base model, they have random and fast for their method. So the random is basically saying I'm randomly sampling a sample from the training data as input context. So in addition to the original question I also have the additional training sampled from the training data set. And then the class is that I'm not doing random sampling. I'm making sure that every choice is being sampled. So here they have four classes they want to classify. So when they sample the training data, they also want to make sure the same number of classes are sampled, so that they know what's the meaning of that class. So when that meaning of that class will help them to decide, will help the model to decide what is the context of 0 or 1 when they try to making predictions on the certain classes. Right? And you can see that from this table, the class sampling ensures that each class is presented in the input sample and can reduce some sampling bias. And it is simply to be very crucial in this method, especially when in the scenarios where the data set might be imbalanced or certain classes are underrepresented. You want to make sure when you put it into the model, your input have the meaning of that class. And then you can also find out increasing the model size. They have the increasing the model size here on the between rows. The increase the model size actually enhances the performance. So larger models, if you move from 8 billion to 70 billion, 7 billion to 70 billion, and tend to have better performance in terms of AUROC. And then both the likelihood method and the entropy uncertainty treats all tokens equally, like I said, but they found out some tokens may carry greater relevance and the representations than others. So later parts, a lot of the papers are dealing with that problem, they're not treating samples equally anymore. Right? All right, so comparing those three methods in the input uncertainty. So you can see all of them are basically changing the input. And if you formulate it into the ensemble or Bayesian way of uncertainty, then you're basically changing the latent distribution for the input. And then you're trying to calculating the epistemic and aleatoric uncertainty differently. And usually people will try to calculate the aleatoric uncertainty after they calculate total uncertainty and they just minus minus the total with epistemic uncertainty. And okay, so I think that is the input uncertainty. We have spent, I think, much more time than I expected. Then any questions for the input uncertainty? Yeah.
The input uncertainty is doing a lot of analysis of the inputs.
Yeah.
That's nice in analysis time. If you have a real-time chat, it sounds like it'd be really slow. You do this up front on test data and then make architectural changes.
No, like I said, all the uncertainty quantification method right now, we didn't cover that. All the quantification do not change the models, the models distribution.
Not the foundation LLS, the overall application architecture. So if you have a multi-agent system, the prompting,
no, I don't think they.
Action would be a new.
Yeah, so like I said, they do not change the model, and you of course you can do it sampling multiple times. Phrasing.
How do you get the benefits of this in a real-time chatbot?
Yeah, so
it sounds like it's very slow analysis. You can't do real time.
If you have, like, say, when you in a real-time chatbot, like you have the certain user input, and you can do paraphrasing for that input and then pass it on to the language model. And language model can do a simply majority voting to give you the final answer that is appearing like as most confident. That would be an easy way to do that.
Okay.
Yeah.
Okay, so that would be the architectural change. Now,
Yeah, the contextual change, not a model change. Yeah.
I never said model change.
Yeah.
The system change.
Yeah.
So then there would be ways of just passing it on. But it would make sense to do like 50 LLM calls for the question.
Yeah, that's the open challenge we're going to talk about later. Yeah.
So, if I would understand this correctly, are you measuring how ambiguous my input is, regardless of the LLM, or are you measuring how ambiguous the LLM thinks my input is?
How to put it this way? So a lot of the papers here, they are trying to quantify the first situation you're saying, like.
And then they're measuring it against the Western.
Yeah, no, yeah, they are measuring against the LM. So that's what I said. It's very hard, like very complicated right now to actually decide whether the uncertainty is actually coming from the input or the model itself. Yeah.
How do you generate variations that are significant? Because if you have the LLMs are good at mapping to the same concept, many synonyms. So, but you don't want to change the input the question from the user so much that you change the meaning of the question.
I think you can change very significantly, but as long as you have the weight on the final
Because you don't want to change the user's question.
Actually, here you can see this method, perturbation module, they just do they reduce some tokens. If your original input is like I'm happy, I'm not happy, then you reduce a not, they change the semantics a lot, right? And then in the end they have this weight on between the similarities of the input and the original input. So if you are changing it a lot, you just downweight it in the final when you're calculating the entropy.
So that's your safety guard.
Yeah.
Radically changing.
Yeah. All right. So then I think we still have a little bit time. We'll have a cover break in 10 minutes. So I'll try to cover this parameter uncertainty methods. So in this section, you will see a little bit like supervised training, either change the model weight or you're changing the model itself. So the parameter uncertainty, the term is like similar to the when my student and I were debating, like they also think about this as an epistemic uncertainty, and they're thinking like that the uncertainty comes from the model itself, and either from the gaps from the training data or specific parameters it has learned. But here I would just try to clarify the models under this category. We're thinking about like they are modifying the model or they're changing the model itself to estimate the uncertainty. So do not confuse, like, is this not where I'm not considering as the uncertainty from the parameter. I'm just considering the model itself has certain changes of the parameter rather than the vanilla LM, so the base model. Other than the base model, we still modify something on the model. So that's why we call it parameter uncertainty. So like I said before, if you have input previously in input uncertainty, your formulation is like this. You change on the input, on the latent input. But for the vanilla deep ensembles, the formulation is in this way, right? So they do not have any like the input, but they're conditioning. They're trying to calculating the theta, which is the weight on the model. So parameter uncertainty would be a natural way to think about that way, to fit into this deep ensemble as the formulation. All right, so we'll cover 3 category of methods. One is ensemble, of course, you have multiple models. And the other way is Bayesian way. And the third way is you supervise training your model and changing the model's weight. All right, so like I said, the ensembles is, if you directly change all the parameters for ensembles, it's going to be very costly. So all of the papers in this ensemble category are going to be based on LoRa. So if you are not familiar with LoRa, it's basically you have the base model and you have a low rank matrices A and B. And when your model make predictions, you are also times with this additional matrix with A and B. And that's going to be with your be your final that output here going to be the final going to be put it into the final treated as a final output, right? And so like I said, the challenge here is because you do not want to have a multiple base foundation model, so you just want some variations of that model with parameter efficiency. And so they are doing the ensemble on the LoRa rather than the ensembles on the multiple models. So this is a very like a simple one, right? So you do, instead of doing ensembles on the base model, you have multiple low rank matrices, right? So on the right, you will see their analysis from this paper. So this is a distribution. You see this like x-axis is the confidence beams, y-axis is the accuracy. So this is a pretty basic formula or diagram for the confidence analysis, whether we can understand whether it's overconfident or underconfidence, right? Like I said, the axis is the confidence beam. The y-axis is accuracy. If you have a well-calibrated perfect model, then your confidence should be equal. The distribution of your confidence in the sample should be like the same as your or close to the accuracy within that beam for the sample within that beam. So there would be an ideal dashed line here. And they found out like the original like exploited ensemble, like if you do not LoRa, you just exploited ensemble on the base models, then you will have the overconfidence issue. It's below the line. If it's below the line, it means like my confidence is over my accuracy. So it's like if you directly do deep ensemble, it's going to be overconfident. And then they doing this LoRa ensemble at this pretty close to the dashed line. It's well calibrated. And but here, this is not doing language model. It's just doing, they're testing it on the CFAR 100 dataset. It's a image dataset. But this idea could also be transferred to the other method as well. And then people think about, okay, how about I'm trying a different way, doing an ensemble. I'm doing the Bayesian ensemble. So the challenge for this previously with LoRa is like it's when you do it on the language, they found out like it's always overconfidence because the model is too big and your sequence is very long. The confidence is going to be propagating. And there's always, even with LoRa previously, it's always become overconfidence, especially when you have a small data set, you try to train and like usually when you train on LoRa, you have a training data set and you want to fine tune it on your own data set, that data set gets comparatively small. So that's the reason why people think, oh, okay, maybe I can use Bayesian to solve that problem, small data set problem, but also giving me some uncertainty estimation. But in Bayesian ways, like if you want to calculate full posterior distribution for deep neural networks, right, including large language models, it could be very challenging. It's intractable. So in order to do that, they usually have these different steps. So in Bayesian inference for classification or token prediction, their goal is to find the full posterior here. And then calculate, like I said, calculating this posterior is usually intractable. And so they are using Laplace approximation to approximate this probability posterior. And then in this paper, if you're using Laplace approximation, then your probability distribution gonna be something like this. It's a pretty standard. Your probability distribution gonna be something like this, and then your goal is trying to calculate this sigma, and this sigma here you will have the Bayesian matrix to calculate, and then here, the Bayesian matrix is hard to calculate as well. So in this paper, they're just using a specific technique called Crocker factored approximator. This is just very classical techniques to calculate, estimate the posterior distribution. So I'm not going to that detail, but basically, they are using the key component is to calculate the Bayesian matrix, and then with this kind of method, you will have the uncertainty estimated in this way. So instead of just having the maximum posterior, and you also have the calculation on the theta, which is the output of the network as well. So this network output is going to be directly used for the uncertainty. And then another Bayesian way of modifying the models is proposed. They are directly criticizing the previous method, is saying that the previous method is still very computationally expensive when you're trying to calculate the Bayesian matrix for these, even for LoRa metrics as well. So they're saying, okay, I'm making additional constraints on this A and B. So previously they are having two matrices, this green one here, but now they're saying, okay, I'm just optimizing one matrix and fixing this matrix as the inverse of this matrix. So they're just optimizing one matrix. It's much more efficient. And compared to the previous one, they're showing that, okay, the performance is getting better. They conducted on 6 reasoning tasks. And then the baseline method is the maximum likelihood estimation, like this supervised fine-tuning method, and also Monte Carlo dropout, and also the deep ensembles, and also the previous one, the Laplace LoRa. And you can see that they reported the performance on Llama 2 7 billion pre-trained weights, and they reported the accuracy and the ECE in percentage. And then you can see that they are achieving the best performance. And also they found out like their method is performing better at out of distribution samples. Here, the out of distribution means like they're training on one data set, which is the OBQA, and then they tested on the smaller distribution shift, which is they're having similar context, but they're also having a larger distribution shift data, which is the chemistry and physical data. It's been much more specified, and they found out like their model is better at when the larger distribution shift happens, right? And then the last category within this parameter uncertainty method is like I said, parameter uncertainty. We're just thinking we're changing the parameters for the model, and they just do uncertainty aware training. So instead of just having one model's output, they also having the probability as a supervised learning training head, and they also like. This is a consistent conclusion found by different kind of method is saying like supervised learning methods seem to perform better on your training data. And also, if it's fine-tuning on the distilled data, and then all the like data you use for uncertainty, like the data set you build for training this data is like you have a answer and you have a confidence from the any like uncertainty quantification method. And then if you use that confidence and this training data to fine-tune your model, and it usually performs better than the previous, like if you do not have supervision. And then they're also saying like you should not just use all the uncertainties, all the samples with uncertainties. You should have some filtering mechanism or distillation in there in this paper. It's saying that I'm going to fine-tune it on some high or some margin. We're treating the answers with margins, right? So I'm not trying to confuse my model with some incorrect confidence estimation. So they're saying with distillation, and their method is much better. So this is the dashed line is no distillation, and the solid line is with distillation. So with the distillation or with the filtering on the uncertainty training data, and then you will have much better performance without any filtering. Right? So that means basically you need to use high quality uncertainty data rather than a low quality data. Right? Okay, so that basically concludes this section, which is you're trying to modify your model's parameter to estimate the uncertainty, either through Bayesian ways, LoRa, or through add a additional supervised learning head to generate the output. All right, so I think that's it for this section. And in the next, after the coffee break, we will talk about the reasoning uncertainty method and prediction uncertainty methods. I'm here for the questions.
Yeah.
Yep.
I think I missed it in the previous slide. What was the method that you used to quantify the inputs? So you said like you're distillating based on some quality metrics, right?
Oh yeah.
Yes.
So firstly, the uncertainty is generated through the token probability, and they're using entropy. And then the distillation is saying, okay, they're acknowledging that existing like uncertainty quantification data is not perfect, estimation is not perfect. So they are only using the correct samples, like their uncertainty is high when their prediction is wrong. Is that clear?
So they have like some ground truth they're comparing to.
Yep.
Ground truth. Okay, got it.
Yeah, you can think of it like they're calculating the ECEs, and then with lower ECE, then they will use that sample. Yeah.
To make an analogy, I don't know if this is something you're going to cover later. In the past, I was running a financial fraud detection group, and I found it was useful to work on kind of a defensive attorney and prosecution attorney. Because normally people assume the worst case, but then you get many false alerts. And so if I would have a defense attorney and a prosecution attorney trying to interpret the situation on, gee, there are valid situations where people could be doing this behavior that looks suspicious, but it's valid normal behavior of people that's not fraud. And what I'm getting into is if you're interpreting, using LLMs to do classification, such like a guardrails kind of thing, then kind of having multiple modes, like interpreting it as a worst case scenario that's that's, for bad behavior and a best case behavior that's plausible but not, bad? Is that anything that you discuss?
I think in the downstream applications, we will have one example closer to your application, which is they're trying to control the robots. They want to involve humans in the loop, but they do not want to bother humans with too many false alerts, like it's high uncertainty. They will have the certain technique to cover that. Yep. Okay. All right. So this is a coffee break. We will be back in at 10 o'clock.
Well, once it's verbal, like, have like thousands of. Wasn't, I think he just hadn't done the work far enough, and I think that's it's kind of like, I remember it's, I feel like he just, that is the organized, that's the way. Organized, we use the science. Yeah, that's what we. But I organize. I think I. Yeah. Okay. Or I organize. Yeah, that's like. I was like, I have to take it. I like kind of tell us different.
Yeah.
Okay, let's get started for the second part of uncertainty quantification methods. So a quick recap. Previously, we defined the terms for uncertainty and we defined the terms for confidence. So confidence is quantifying a specific output generated by the language model given a certain input. And uncertainty is I'm quantifying the diversity of all the possible generations given by the language model given certain input. And then we talk about the specific challenges in from traditional deep learning methods to language models. Those challenges are like the language models, they have very large parameters. It's very hard to duplicate multiple foundation models. So that motivates people to do a LoRa ensemble. We talk about that in the first session for parameter uncertainty. And then we also talk about the challenge in language model uncertainty quantification is like the input is pretty open. You do not have a very clear, sometimes you don't have a clear definition on or clear representation on your input. So it's input ambiguity. So that's the reason why people perturbating the input to ask for clarification. And that's the first kind of method in UQ we talk about. It's input uncertainty. And then we talk about in this session, starting this session, we will talk about the reasoning uncertainty, which is something I'm really excited about. The reasoning uncertainty is more concerned with the reasoning steps towards one final answer. And then after the reasoning uncertainty, we'll talk about like very general, like other techniques in prediction uncertainty. You do not need to stay on with the reasoning steps, but what about a general generation of your sequence? What about their uncertainty? So that's basically the last category is something that we cannot find a good home for them for these three categories before. All right, so let's talk about the reasoning uncertainty. So the reasoning uncertainty here refers to the variance that exists in the reasoning chain. So if you talk about reasoning, it's like you have certain steps, and different steps are connected towards to the final output. So for example, on the right-hand side, we are visualizing three possible reasoning processes when a longer model generating their outputs. So we can see that they are likely to happen like at different reasoning passes, even though they have the same input, and even though sometimes they are having the same result, the final result, the same final result. And then this is basically coming from the nature of reasoning, because the multi-step reasoning, you can have different steps. And if you sample it multiple times, say if you think chain of thought as a way of how models think of things, then if you sample multiple times, the generated chain of thoughts are also different as well. So it's also debatable whether it is aleatoric or epistemic, so I won't differentiate it here. But if you think about if you like admit that the task have multiple valid passes, and sampling sampling randomness on the reasoning chains could be considered as a aleatoric uncertainty. But if you could also argue that if the reasoning has is like naturally flawed and due to poor training or lack of reasoning data, and you can also think of it as a epistemic uncertainty. So it's very hard to judge whether the uncertainty happening in the reasoning process, is it because the data of the model, right? Okay, so in this, under the reasoning uncertainty methods, there are two main categories. The first one is the content level. So we just treat all the reasoning steps as a paragraph, measuring their content, the divergence in their content. And the second one is what I'm mostly excited about, is that we measure the structures of the reasoning steps. All right, so we talk about the specific the reasoning, the general idea of reasoning, but basically there is one view of showing defining LM reasoning is like different from the direct output, which just give you an answer. The reasoning-based generation from the longer model is something like on the right-hand side is chain of thought or iterative reasoning. You can also have other specific like techniques or graph of thought, tree of thought, this kind of techniques. But basically, you are trying to generate the final answer through some intermediate reasoning steps. And when you generate the intermediate steps, you sort of you gradually or you frequently revisit or revising your prior outputs and progressing to the subsequent reasoning stages. And you're probably going to explore multiple reasoning passes on trajectories until you get the final output, confidently get the final output. Okay? And to better deal with the problem, like understanding the reasoning details could be a helpful thing. So an interesting way to understand the reasoning process could be using the Markov decision process concept to explain it. It involves an LM and the process reward model, the state, and the reasoning steps. So the LM policy here operates by generating tokens, and which forms the higher level reasoning constructs. And the state here is gradually expanding. It's represent the sequence of reasoning steps so far, and the actions correspond to the selection of new reasoning steps, or in the final step is selecting the final answer. And the process reward model, the PRM, provide feedbacks or estimations on the quality of your reasoning steps and the final answer. So by optimizing the policy, the LM, to maximize the reward, so the language model can be guided by the process reward model to generate accurate and meaningful reasoning steps. So based on this, we could roughly divide the reasoning process of uncertainty quantification into two aspects, which is one is content aspect, and you just treat all the generated sequences as a paragraph, and then the second category is you want to quantify the reasoning, the variance on the reasoning structures. So let's firstly talk about the representation for the reasoning process. There are different ways, like I said before. If you just do directly output, it is simply just one, you can think of it just one tree with the root node and the child node or the leaf node. And then if you do chain of thought, is a sequence of outputs. Each node here is maybe a sentence. And then you have self-consistency chain with chain of thought. Then when you get the final output, you do the majority voting before you get the final output. And then there are also like tree of thoughts or graph of thoughts in a step. So let's take a look at a very specific example here. Basically, that shows the uncertainty in the reasoning process. Say I'm asking the question, if there is currently summer in Australia, what season is it in Canada? If you ask this question to a language model, here I think they're using GPT-4 when they're asking this question, and they're asking to generate the reasoning steps. So there are specific reasoning steps. The first one, this left-hand side, this reasoning structure is something like this. So each age, they ask the language model to generate the sub-questions as age, and the nodes in this to this sub-question would be considered the answer to the sub-questions would be considered as node. So the age question, for example, in the first, in the orange line here is going to ask, where is Australia located on Earth, right? And the blue question, the blue age here is, where is Canada located on Earth, right? And then they have the nodes as answers, saying Australia is located in the southern hemisphere, the Canada located in the northern hemisphere. And then these the third question in this reasoning chain or reasoning graph is what is the geographical relationship between Australia and Canada? And then the answer to that question is Canada and Australia are located in opposite hemispheres. And then the next question in the reasoning chain is how does the tilt of Earth affect the seasons? And then the answer to that question is the opposite hemispheres experience opposite seasons on Earth. And then they ask the final question, what season does Canada based on the above reasoning? And they will give you the final output as it's winter in Canada. So currently it's summer in Australia, then the final answer is it's winter in Canada. Right? So this is one chain, like a structure of reasoning. And the other structure of reasoning, one possible structure of reasoning is like something like this. So they also ask which hemisphere is Canada located, which hemisphere is Australia located, and then get the answer. And then the second question following that previous question, that the location on the hemisphere, and they're going to ask when does summer occur in southern hemisphere? And then they ask when does winter occur in the northern hemisphere? And then they ask how does the seasons in the northern hemisphere compare to the seasons on the northern hemisphere? And then they get the final answer, it's winter in Canada. So it's like slightly different reasoning path compared to the previous one, right? And then another reasoning path could be a little bit blurry, but I'll just read it. So the question would be like, why there be seasons on Earth, and then how the season are affected, and what season is it in Canada if it's summer in Australia, and then what is the season that Canada is based on the above reasoning. So they just ask like straightforwardly. Right? So that's you can see that with the same question, even though they have the same final answer, there is different the variabilities in the reasoning path. Right? And then let's talk about how do we quantify this variability in the reasoning process. The first one is content level. Like I said, you just treat your language, the generation of the reasoning content as a paragraph. Right? And you can just compare the semantic variability between those paragraphs. That's very straightforward, right? And then in this paper, they're doing something more. They're not just comparing all the paragraphs, all the content in the paragraph, but they are extracting the keywords or the key components in the paragraph, because some of the words, like we said before, some of the tokens, they are not that important. They want to extract the important keywords first in the reasoning path, and then treat that keywords as a new like dense paragraph and compare the variability or diversity or entropy of that paragraph. Right? So it's something like this. So think about like yeah. So the next question would be how can we evaluate the uncertainty or diversity of a paragraph? So simply sampling explanations, like I said before, is not enough. Like some explanations, even though they are like syntactically correct, but they are not logically stable or truly explain the data. So in this way, this paper extract the keywords first, and then the sample the explanation based on the weight on each of the token. And then they also, when they compare the similarity between the paragraphs, they're using the entailment probability. Say they're not just comparing the like cosine similarity between two vectors of the final output. They are using another like natural language inference model to compare their entailment probability. And then that entailment probability basically says if this one is true, well, that the other one be true. So this probability will be used. Right? And then I think this is their result here. Like I said, their findings show that not all the tokens are very informative. So on the left-hand side, if you visualize all the token sequence, all the tokens probability, and then based on their correctness or incorrectness, you will see their density distributions is not that differentiable. But if you are showing some using the entailment probability, and then you're basically having two like slightly much different, like have more difference than the previous one, and so showing that not all the logits are helpful. You should considering the semantic meanings of the sentences, well, not just considering the logits, right? And they also conducted a ablation study where they do not use entailment, and they if they do not use entailment, then this is this method. And if they use entailment, and this is the method, they show that this entailment is pretty helpful. Right? And another way, similar way of doing this is like I said, I think this is already explained here. But the second category of reasoning uncertainty methods is called the structure level uncertainty quantification. So why do we care? Like, what's the difference between two paragraphs and a structure? So think about this way: when you're trying to reason on the final for the final answer, then if you treat it as a paragraph, then your paragraph is sequentially, right? So this question appears before this question. But that's not that it could not be also possible that this question appears before this orange question because they are two parallel questions, right? So the sentences appear earlier in the paragraph. That does not necessarily mean they are more important, right? If you are using a graph structure to represent that, you can disentangle the locations of specific steps, right? So think about this question could be appearing before this blue question and this or after this blue question because they are parallel on the reasoning steps. But if you are using a paragraph to concatenate them all together, then you are having the orders, and this order is going to make a difference, right? And that's the motivation, basically, why the topology of reasoning steps is more important, because when you try to quantify the uncertainty, you want to make sure those parallels, they are considered the same, right? And so that in this paper, they introduce these methods. Firstly, of course, they are forming topologies first. And they are by forming topologies by asking those two questions, like say, given this question and reflect and generate knowledge points or sub-questions, what sub-questions should I generate? That sub-question is going to be used as ages in the topology. And then given this sub-question and provide a precise answer that is the node for that question. And then they'll have a third step to concatenate or to link the relationships between different nodes and ages, so that previously they are having those sub-questions and answers, and then they have those pairs, and then they try to connect them all together between nodes. And then with this connection, you will formulate a graph here. So with this graph, then you can calculate the variability of the graph based on graph added distance. So that's a very straightforward way, right? How can I move certain nodes to a different place or change certain nodes' content so that those graphs are identical? So that calculates the graph added distance, measures the similarities between two graphs. And in order to do that, because the nodes and ages now, they are questions, they're not just numbers. They are text, so you have to embed the semantic meanings first. So you want to maintain the semantic meanings. And then first step is to do semantic embedding, and then they just do the reasoning distance calculation from topology using graph added distance. They defined in this way. So there are two costs of modifying the nodes and ages. So the substitution cost is if I'm substitute certain ages, what is the cost? If I substitute certain nodes, what is the cost, right? If I'm manipulating this node with another from another node, what is the cost of manipulation? So that is its substitution cost. Or there could be a deletion or insertion cost for nodes and ages. So this is what they defined. And then they calculate the graph distance for the reasoning uncertainty. With this graph distances, you can think of like if you have 20 reasoning steps, 20 reasoning graphs, and then you will have 20 times 20 similarity metrics, right? So with this similarity matrix, then you can calculate the uncertainty out of it, right? And this is the result. So they have pretty interesting findings here. So they show they do not use the ECE like the calibration error or a UC because there is no good like golden answers for the reasoning steps. And then they just do the correlation through faithfulness. Like the correlation with the ground truth faithfulness score reviews how much the model rely on this complete reasoning passes. And this value reflects the correlation. The values in the table reflect the correlation between uncertainty and the ground truthfulness. So a more faithful LLM performs, and the less uncertainty it should be. And so by the UQ method, we can observe a more negative correlation for well-behaved UQ method. So they mentioned that the reliability of this work is based on the successful rate to generate legitimate reasoning topology. And this results show that their method is much more effective, revealing the UQ's real faithfulness. So the baselines they're including is just chain of thoughts treated as a graph, the paragraph, and compare their embedding distances, comparing their entailment similarity distances, or using the NLI model's logics to calculate the distances as the uncertainty. And then this is their methods using the similarity matrix to get through the graph edit distance. And they also have a very interesting finding. They did so with these topologies specified on the reasoning step and comparisons between the reasoning steps, so they are able to further analyze the redundancy node for a certain graph. So the redundancy rate of a reasoning path, it could be measured now. So they show that the GPT-4 O-mini has a significantly high redundancy rate in both nodes and edges. And one possible explanation might be like the high accuracy of this GPT-4 mini model is coming from a broader searching space, so that they are generating more nodes and edges. But this also reflects the potential to reduce that optimize this reasoning process for GPT models if you are having the cost constraints. And comparatively, the DeepSeek model here on this hand side is much more that their redundancy nodes are much smaller, much less. And it could indicate that the model training process is conducted with some special design to encourage the valid reasoning, so that which eventually contributes to the final output. They also have with all the reasoning passes specified, topologies specified, they also do a clustering algorithm to find out some whether there are some common reasoning strategies generated from long-range models. So they have do the k-means clustering, I believe, and they have, I think they're in this table, in this figure, you will have you can find 4 clusters mentioned, and 3 of them are look at the 3 of the clusters and found out the explanations or understanding for the certain cluster. So the red dots here, this cluster is this completion based. This more straightforward from the top to the end. And then the second type of I'm saying something wrong. So the green dot here is the forward reasoning, which is just doing by not actually performing the actual reasoning, I believe, because it's just reading the original node, original question, and generate the subsequent answers directly. And the second step, the second paradigm here is what they believe is the humans look like is thinking. The second category is called forward reasoning, and they have tried to recall the knowledge points and narrow down the range, so to find the possible answers in a thought train. And the third one here is more a mix of 2. So it has steps to ask for the characteristics, but also try to reflect it if it has been if this question has been seen before in the reasoning steps. Yeah, so that's basically this kind of reasoning passes. So like I said, I'm personally very excited about this one because firstly, it has, I believe it reduces some redundancy in if you just then these paragraph-based ones. Like I said, the language, the location of the certain sentences or certain reasoning steps appearing in the whole reasoning process does not necessarily mean they are much important. And I believe with this kind of method, you can analyze the topology or reasoning steps better. Later, if we can assign rewards for certain nodes in the reasoning topology, maybe we can have emergent capabilities of language models in doing new type of reasoning rather than aligning with human reasoning steps. Right. Okay, so that's concludes the section, the reasoning uncertainty measures. Any questions on reasoning? Yep.
So for the last part, I mentioned about structural reasoning paths or structural reasoning graphs. I wonder if it'd be beneficial to look at them in the reverse order, because the idea being that regardless of how you're starting out, conceptually, to be able to answer that question, we should the bottom reasoning nodes or the bottom concepts should be very similar. So instead of going like how I started from, and because if you were to prune the top first, I think from my perspective is almost irrelevant as long as you should end up in the same path. And then if you take the subgraph, which is the bottom part of it, and then embed it, you can find other similar paths to that as well.
Yeah, so I think I'm trying to clarify this. The uncertainty they quantified is for between the topologies, and after the quantification, each topology or each reasoning path will have a final like confidence, and this confidence, I think the reason why they are looking at from top to bottom is because they believe the final confidence gradually increase as your reasoning path grows.
But if you're doing like, let's say, jump distances from nodes, if you're starting out with way up here versus you're starting from way here and you both end up the same place, your distances from the nodes or your algorithms that are comparing distances
I think to answer that question, I think it's mainly because they have the final answer may not be the same, but the questions they ask are the same. So it's easier for them to compare if they're starting from the same place, right? Because like I said, they have different reasoning paths. It's not guaranteed the final answer are the same after different paths.
Could you say again how the reasoning steps are extracted from the LLMs? Because I think there's evidence that suggests that when you, like what the LLM outputs is not necessarily a true reflection of how it reaches the conclusion. So is that like an assumption of the approaches, that they take the output from the LLM, which may not necessarily reflect how?
Yeah, so I think for their for this paper, their prompt is something like they first I think they're positioning as LM explanations rather than the reasoning steps. So they first let the LM generate the answer, and then ask given the question and answer to the language model, and ask this to generate the reasoning steps for that answer.
Which would then assume that it can actually spell out what is important in this reasoning process.
Yeah.
It
So
could be like a difference, right?
yeah, it could be different. I think it's a limitation for this. Yeah, you're right. Yeah, I think I've talked to the other researchers. I think there are different ways to represent a reasoning path. It's just their way. So feel free to use other way of doing that. All right, so then let's move on to the last category of the uncertainty quantification method, that's the prediction uncertainty method. This meant, like I said before, this category of methods, they are pretty general. They might not fit into a specific domain. They're not actually manipulating inputs, or they're not manipulating the parameters. You'll find those a lot of the methods are following this similar recipes, but in different ways, right? Okay, before we formally introduce the prediction uncertainty, let's talk about an example. I think we already know like the outputs from the LMs, they could be different. They could have some errors, even you have the same question due to decoding strategies like a temperature or the autoregressive procedure. And then the sim model may have different answers. So since this is the final output from the language models, one general question we ask could be like, how can we obtain the uncertainty using output from LMs? And here in this section, we'll talk about specific methods to get the final uncertainty, not just a broad, like general term, like the diversity, and how can we actually calculate the uncertainty with some mathematical equations.
Would you mind closing the pop-up in the top title?
Oh.
Right, there's X to turn up the volume. Turn up the volume in the top center. There's a small X.
This one?
Yes.
Okay, great. Okay, so under given this idea, like they define these as prediction uncertainty as the uncertainty that directly measured the output on from the LM. So one key insight we'll see in this direction is like it's a sequential output nature of LMs brings new challenges, but also new opportunities for uncertainty quantification. So the first category of methods for prediction, the final outputs is the single round generation. So if you do not do multiple samplings, you just have one sequence generated, how can you estimate the uncertainty? So before we're going to see the technical detail, let's first see the key idea of single round generation method. Recall that previously we defined the uncertainty focused on the predictive distribution given a question over all the possible generations. And then the confidence focuses on the predictive distribution over an answer given a question. Here, since we only generate one sequence, like single round generation, the assumption here is your confidence from one certain output can reflect the uncertainty. One easy way from the classification, traditional classification method is like you just use 1 minus the confidence of your probabilities output, and then treating that as your uncertainty. I assume that it's not perfect, but it's when you have like limited computational overhead or the token limit, like one time uncertainty is also doable. And like I said before, one way to do to represent uncertainty is entropy, right? So we already talked about the sentence level entropy. This is a white box one, and we also talk about token level and entropy. And different from the entropy, another method people would use is perplexity. It's especially designed for the sequences like language. So for perplexity, we could use the sum of the probabilities of the new generated token to calculate it. At every step of the autoregressive generation, we sum their log probabilities. And then we, after all of that, we take the exponential out of it. So normally the perplexity could be thought as how surprised the model is about the generation. So it is natural to think higher surprising results indicates a higher uncertainty here. And that's, like I said, this perplexity is specifically designed for the sequence modeling. But previously, we also talked about all the other possible probabilities. You could do like if you have probabilities, then you can do multiple ways treating this generation from one sequence and use that as your whole model's distribution given that input. Okay. And one specific way, like I said before, people have found out that not all the tokens are very helpful. So how can we help integrate that insight into the quantification of your model? Like this method is called SAR, or shifting attention to relevance. So they found, like we said, irrelevant tokens might have the largest entropy in the calculation empirically. And however, this irrelevant entropy should not be considered too much. You should just consider the dense or the most informative one. And to overcome this issue, and this SAR, so entropy with shifting attention to relevance, provides a weight to the entropy instead of just using the original token entropy here. And then they're assigning certain weights to these entropy of each token. And how can they calculate, how can we define certain token is more important to another than the others? They just do by removing certain tokens out of the sentence and calculating the changes on the semantic meaning, right? So you think about it, you have the original sentence, output sentence, and then you feed that into a model, get a representation, and you remove the sentence, the certain token here, and feed it into treat it as a new sentence, and feed it into the model, get the representation, and calculate the distance between those two. Like this basically measures how when you delete certain token, well, that change the similarity with the original one, right? So that's how they assign this weight through this equation here. And then with this entropy, you just calculate the weighted entropy of all the over all the tokens in the sentence, treated as your final uncertainty. Okay. And this they compare with the original token entropy, and they found out like it's getting having higher. I think it's here is reported AUROC. It's higher, the higher better. So that the token level entropy with SAR shows a very comparable like improvements like on multiple rounds of generation baselines. So then they also compare with the P2. Remember, P2 is just asking the language model to explain or to estimate this confidence by itself. Like here, P2 is the probability of I know the answer. You have certain prompts to ask whether they know the answer or not. If you're doing a white box setting, oh, I forgot to mention, all the uncertainty quantification methods if they have the white circle here, they basically mean that they are white box. They have a black circle here, it basically means they are black box. So for P2, you have both white box and black box implementations. So if you are using a white box method, basically you are just asking, yes, I know the answer or I don't know the answer. You just measure the I know the answer and I don't know the answer, the probability. But if you do not know have access to the probability, just sample it multiple times and then just do an Monte Carlo estimation. Okay. So these two kind of methods, the P2 and the token SAR, the token entropy falls in the category of single round generation. You only have one sequence generated from the language model given a certain input, and how can you calculate uncertainty out of it? That's a two method: self-evaluation through P2 or through the token entropy, right? And then the second category is widely used, mostly the black box uncertainty quantification method for language models. They are using the multiple rounds generation. This also falls into the similar idea as ensembles. You have the multiple generations, and you just calculate over all the possible answers to get the estimation on the probability of the distribution of a certain answer. And with this distribution, then you can calculate the uncertainty out of it, right? But it's hard to get if you have a black box setting, it's really hard to get this joint probability of a answer. And then but of course, if you have like access to the model, then you can just use the probability-based estimation. Like I said before, the predictive entropy is the joint distribution, joint probability distribution over all the samples you get. So for each sample, you can calculate the sentences probability through the joint distribution of words, right? And then you calculate the expectation over all the possible tokens multiple generations you get, right? And this is their predictive entropy, like people call it as predictive entropy here. So both experiments they're conducted on the 52 billion model from Anthropic. And from the left figure, the green boxes show the correct samples, and the blue boxes show the incorrect samples. So the x-axis is the entropy with forcing certain beans, and the y-axis is the count number of samples. And from the left figure, this is one that I believe is on Trivia QA, and they could see that the correct samples tend to have lower entropy, and the incorrect samples have higher entropy. So the higher predictive entropy is mostly wrong answers. On the right figure, it's the human evaluation results, and we could also see that the samples with high accuracy also has a low entropy. So the x-axis is the entropy, y-axis is the pass rate for the certain sample. So this is basically the introduction for this predictive entropy. You can also, of course, have like multiple variations for predictive entropy. Like you can assign weights to certain generations of the outputs. You can combine it even with input probability, input uncertainty quantification methods. So you variate your input and assign weight for the final output. As long as you have multiple generations of the from your model, then you can use this multi-round generation uncertainty quantification methods. And then let's talk about the third category. So previously, all the multiple rounds generation, they do not rely on existing like another external model to help them do the quantification. But there are some other methods. I think it should also lies within this category, but we separated because they're using an external model to help them define the uncertainty. So like we said before, in the traditional classification models, like we can see that assume this is a black box setting, and we sample the model to get 4 pandas and 1 dog. Then the frequency of pandas is like 4 divided by 5. So the simple way to get the uncertainty is using the highest frequency is the 1 minus the highest frequency is 0.2. But for LMs, the class labels are not predefined, right? So you are not just as clean as these class labels. You are having this like variations on certain type of the outputs. And for example, this one you have 4 pandas and 1 panda. Maybe they should be the same actually. But if you're just comparing them without semantic meanings, then you just treat it as 0.8. But if they are considering the semantic meanings, then the higher frequency is 1, right? And so the reason why people are using external models is to use the external model to help them to judge whether those two certain outputs are semantically equivalent. Right? So if you have a external model like entailment or another long-range model to help you judge whether those two generations are semantically equivalent, then you can feed that into predictive uncertainty by assigning certain weights on certain outputs, right? So there are two kind of methods we are introduced here. but the key idea for them is, like I said, they're using an external model. Most of them are using natural language inference model because it's relatively stable and it's also have a good generalization capability in understanding the semantic meanings. And they use this external model to evaluate the semantic relationships between each pair of the responses. So, like I said, we're going to talk about two main type of method that use this external semantic model. First is the distribution-based entropy methods. We will talk about semantic entropy method and the kernel language entropy method. And we also talk about another kind of method is pairwise similarity based methods. All right, so the first one is the semantic entropy method. It's also a very classical one because they are considering the semantic entropy, the semantic meanings. So the big idea of this semantic entropy is to calculate the entropy in the level of classes, semantic entropy classes or semantic classes rather than each generation or each samples. So they have a step. Additional step is clustering the generated samples into clusters. And to get this class, so the semantic entropy firstly define a concept of bidirectional entailment. So if there's two answers, they're bidirectional, bidirectionally entail each other, then they should be considered as the same, belong to the same cluster. So you can apply different kind of clustering methods to cluster the input, like from 20 answers into maybe 2 clusters. Then with these 2 clusters, then you can calculate the probability of the semantic class, and then calculate the semantic entropy with the final output here. You'll find it's very similar to the previous one, but here it's cluster entropy rather than the specific generation like answers. Previously we are having S as one generated sample, but here we are having the probability of a cluster being generated given S. So this over the cluster. The example is showing here. So if you are having this input, like what is the capital of France, then if your answer is 3, like Paris, it's Paris, London, and then if you're directly using the entropy of likelihood, then you can get in this way, right? So 0.5, 0.4, 0.1, you get their probability. And then if you're using semantic likelihood, then you're just you're treating this two as one cluster, and you're calculating the cluster's probability, right? So the probability of this cluster is 0.9, and then when you calculate entropy, it's much lower than the previous one, right? And they also compare with the entropy and P2 and their AUROCH much better on the trivia data set. Okay, so think about like in this semantic entropy method, each sample or each generated answer will be assigned with one cluster, right? But if you're doing like unsupervised learning, there are multiple methods that can help you to do the soft clustering, right? So you do not need to assign the weight, the labels for the certain clusters. Each sample could have certain probabilities of belonging to certain clusters. So in this kernel language entropy method, instead of just using a like each generated sequence belong to one sentence, one cluster, or the clusters are like mutually exclusive, they're defining a similarity matrix between the clusters, so that the clusters could have some certain overlaps. And then if you think about the similarity matrix between the clusters, the previous semantic entropy is just having the diagonal matrix, right? So they only similar to themselves. But in this method, they are trying to calculate similarity between the clusters as well. So it's no longer diagonal, and the values every 2 clusters, they could have a similarity here. And then compared to the semantic entropy method, this method is having much better results in AUROC across different methods. Right. Okay, so previously in this category, like they're using like in the semantic entropy method, they're having the clustering at the final at the middle step. But we could also free from this manually manually clustering them at this additional step. We can just calculate the similarities between the generated answers and directly apply the spectral clustering or the eigenvalue decomposition to decompose this matrix into certain clusters. And the divergences between the clusters in the similarity matrix could just be the indicator for the uncertainty. So this is one way of doing the quantifying uncertainty through the pairwise similarity matrix. The pairwise, what I mean is pairwise similarity between every generated answers. You do not need an additional specific step for clustering. So here, a difference, like I said, between this kind of method, pairwise similarity methods, and with semantic entropy methods is like they put it cluster similarity into a node similarity, and we can think of this way of a graph. So each answer is a node, and you want to calculate the similarities between the answers, and the distances between the nodes are each node is an answer, and the distances between the nodes could be considered as ages, right? So the weight of this ages represent the semantic similarity. So ideally, if you have a dense, tightly connected graph, then you will have a low uncertainty. But if you have a sparse, dispersed graph, then it's high uncertainty, right? And this is how they calculate the uncertainty through this pairwise similarity method. So firstly, like I said, they still need to generate the answers, and the reason why they fall into this category of methods, external model, is because you're using an online model to calculate the semantic similarity for each pair of the generated answer. Then they calculate a semantic weighted adjacency matrix. And then they construct the graph Laplacian. This L is this equation, this identity matrix, and the distance, the inverse of the degree matrix. And then they can use this eigenvalue on the graph Laplacian to represent the uncertainty. So they have different ways of defining uncertainty with eigenvalues or the traces. And then I think they're finding this one is the best one, the eigenvalue with the defining by the sum of all the eigenvalues, 1 minus all the eigenvalues to get the uncertainty. So they have a analysis, I guess, for the distribution of the eigenvalues here. So for this question, I think the question is Dave and Roger were in which rock group? The answer is Pink Floyd. And then the eigenvalues, I think they're using 10 out of it. And you can see that if you the y-axis is the eigenvalue, and if you sum them all together, and they're finding that those two eigenvalues, the first two eigenvalues are much more important than the other ones. So they're using these two as the cutoff threshold here. So they're using M as 2, and those two are more differentiable than the others, right? And the results show that if you're using definition, like they have different definitions, right? So the eigenvalue ones and the eccentricity and the degree matrix is much better than the traditional semantic entropy method and the p-true method. So here, like I said, they are using an AI model, but they are constructing a semantic with entropy adjacency matrix. They're basically saying the similarities between those two answers should be like, if I'm similar to you, you should have the same similarity to me, right? But in the language models, it's not really the case. So if you're thinking about entailment, or the output of an AI model is three-dimensional. Like it's not just more than just similarity. It's entailment. Like one can entailment two does not necessarily mean that the P can entailment Q, but does not necessarily mean that Q can entail P, right? So in this kind of method, DUE, they're considering the asymmetric similarity matrix, which basically says considering like this asymmetric similarities or entailment relationship between two answers, two sequences. And then in this, like I said, the problems with the previous method is like they're using symmetric similarity matrix. That another drawback of the previous method, like they're calculating the similarity between two answers, but the two answers could be very different. Even though they're answering the same question, the word level semantic meanings could be very different. Say for this example here, the question is how many students become heroes? Then the answer they're having is Andrew and his two friends. And the second response is Andrew Wills, Chris Wills, Reese, and the third response is these three. So you can see that if I'm giving you random two sentences, this sentence and this sentence, you do not think them as related, semantically related, right? The reason, so they're thinking, okay, when we compare those similarities between those two, you should also include the questions in to compare, to get when you compare the similarities, so that to provide some context on this similarity. So like I said, their solution is they're not just using semantic metrics, they're using asymmetric. You can think of it as a directed graph, like with weights. And then with this directed graph, you're not. It's not easy to do graph Laplacian. You have to do random walk Laplacian, which is formulated in this way. And also they're using eigenvalues here in a similar way. And like I said before, you are not just comparing the traditional answer. You are comparing on those kind of answers. So this answer is generated by feeding this question and this answer to complete the sentence. And so you can see the first answer, the first response now becomes Andrew, and those two names became heroes. And the second response now becomes these three students, their names became heroes. And then the third answer becomes like these three students became heroes. So that when you look at pairwise similarities, they are more connected rather than previous one. It's really hard to judge whether they are entailing each other, right? And they do a visualization as well. So this in this case, they are having 20 responses. And each response, the green one, or the black one is the original answer, and the blue one is the augmented answer with the questions. And you can see left-hand side is the original, like similarity matrix. And the right-hand side is the augmented responses probabilities. And this one is the difference between those two. You can see that a lot of changes happens on the third response here, and the final response here. It's mainly because the third response is this three. This three is really different from the other ones in the original response when you calculate similarities. But the last one is also like they have like after they say Bob baby's life, this sentence is having irrelevant context, so it's also very dissimilar to the other ones if you consider original responses. But if you are augmenting it, then this is the output. It's pretty similar to the other ones. It's much easier for you to compare them. Right? And this method can be easily used or integrated with the previous method. Like previous method, they have eigenvalues, eccentricity and degree metrics. This one can be easily integrated with different kind of existing methods. and they all improve this performance. So the on left-hand side is theory method, on the right-hand side is the baseline message performance. And this line here is just with this baseline method, add on their asymmetric similarity and the claim augmentation, the augmentation of the answers. All right, so finally, we are summarizing all the uncertainty quantification methods. In the survey, you will find this table. All the methods I introduced is part of the table, and in the table you will find different similarity uncertainty settings, and how they are generated is influence their efficiency, and whether you have access to the model or whether they can generate confidence along with the uncertainty. Right? So I'll just pause a little bit here for questions, and next section going to be talking about confidence estimation.
So I have just a quick question. In the last section, the multi-round generations of prediction certainty, we have the black box and the black box. By black box, you means full access to the model, or just the probabilities of thinking, for example?
So in this method is probabilities, but in the previous method, some of them are requiring the full access to the model. So like parameter based uncertainty methods, they are having access to the full model.
Yeah, because some of these cloud providers, they are also give you the token probability, but not for the data.
Yeah. So in some papers, you will find them, they call this access to the logits or the probability as gray box, but here we just treated all categories as a white box. Yeah.
A key component of this is measuring semantic similarity again. What's the importance of ensuring that the semantic space of the semantic similarity model is the same as the semantic space of the LLM?
Can you repeat the question?
So what's the importance of ensuring that the semantic space of the semantic similarity model is the same as the LLM? Does that even matter? When you're seeing tokens, your LLMs is thinking them in one way, and the semantic similarity model is putting them together, maybe thinking differently.
Yeah.
Does that even matter?
I think we can think of it as a language, the characteristics of language. Like we humans, we understand language not by logics, but by their semantic meanings. So I guess that's the reason why for the predictive methods, they are considering the semantic meanings.
So the underlying assumption is the semantic similarity model and the LLM are inherently learning the same semantics.
Yeah. They are assuming that. Yeah. Yep.
Is there any benchmarking studies to compare these different techniques?
Yeah, so I think in the paper we talk about something, but I didn't cover that in this tutorial. I think one of the notable papers is I think from last year NeurIPS dataset and benchmarking paper. You can find that in the survey as well. But I feel like I have the same confusion as you as well, because sometimes they're reporting ECEs only, sometimes they're reporting AURC. Some papers they're reporting the correlation with faithfulness. It's really hard to judge what method is performing the best, especially when you have multiple different data sets, right? So I think it's worthwhile to conduct a benchmarking experiment. But I will mention that it's actually challenging to do evaluation, and I'll talk about why it's an open challenge in the last section.
Is there a section on papers with code that would have a topic of uncertainty calculation? Is that a lot of times the papers with code has leaderboard, or the same metric they show many papers increasing over time?
I don't think there is a leaderboard here, from my understanding. But like I said, it's worthwhile to do it. Yeah.
Well, an idea if you want to create. If you're doing good surveys and.
Yeah, I like my students, and we were trying to do that. Well, we are developing our own, because we're having like different kind of methods in a repository. We're trying to reunite them, formulate them in the same code framework. So a little bit hard, like it's a little bit hard, but it's worthwhile to doing that. Yeah. Okay, so let's move on to the section 4. It's about confidence. Like I said before, the confidence is just measuring depending on both the input and the specific response. A lot of the methods you see here, they're already covered by the uncertainty quantification method as well. So there are two main directions, like I said. One is using the base language model's own perception, it's self-evaluation, or this logics to its confidence, or this using consistency, like you generate multiple times, or you're calculating the consistency of the sampled responses. Right? So two main considerations in the evaluation, like it's the same as the uncertainty quantification. They are also using AUROC or ECE. So that's the reason why we just like leave a very short time for confidence here. So one thing to do confidence evaluation is to ask them to self-evaluate, right? So when you generate an answer, what is the confidence of your generated answer? You can ask them to verbalize their confidence. And there are three variants here. So self-probing is like ask for the answer first, and then ask for the confidence separately. And then the top K is like asking the top K answers and their corresponding response, and then normalize it. And then the last one is multi-step, verbalize the confidence in each reasoning step. And from the confidence to uncertainty is you have different ways to mitigate that. This paper is just taking the average of multiple verbalized numbers at the final uncertainty. And we already showed this figure before. This P2 is just ask a language model to estimate the probabilities of their answer is true or false. There's binary classification. And you can use the logics on like true or false as the probability. And you can also strictly use black box setting where just ask it multiple times. And then we also have this sequence likelihood, the joint distribution of these tokens. And variance here is token SAR, like this we talked about before, this semantic attention score from the previous token level logics. It basically reweight the logics with their importance. And the other one is to use the attention score directly from the base language model. This is a white box setting now to reweight the logics. Right? And from this one, some sequence likelihood is just the foundation. Like you can, with the sequence with the confidence of each generated sequence, then you can generate uncertainties such as entropy. So like I said, the one's representative confidence estimation method here is the token SAR. Not all the tokens are treated equally, and you have to assign each weight for certain tokens. And then by assigning weights, you're just removing, what I mean is removing certain tokens and get the changes on the similarity between the original output and original input and the removed new sequence. Right, and then the problem of removing certain tokens, like I said before, can lead to like unmeaningful tokens, in meaningful sentences or broken sentences. They are like out of the distribution of the NLM model. If you're using NLM model to judge the similarities between two sequences, and then this method is saying, okay, we're not removing those things. We're using we are having access to the model weight itself. And we just are using the model's attention as weights. So two ways to generate the weights is one thing is ask a language model to evaluate its response. It's also self-evaluation. And then you can just directly use the next token attention weight as the weight for the certain token. All right, and then we also, to this point, the method we discussed so far have on the model to judge its own confidence. For example, through the output abilities or by directly asking it. But now we will switch to a different paradigm, is sampling-based method, like we sample multiple times. The core idea here is to ignore the model's internal perception directly. It's a black box setting now. And we just generate multiple responses from the same input and then estimate the confidence by looking at the distribution of those answers. So they have like two like advantages compared to the previous one. That you do not have access to the logics. It's black box setting. Also, it depends on less on the model and so on. Sometimes it's like the model is not reliable to estimate itself, evaluate itself. So this example here is the majority vote. So it is a like key component of self-consistency paper in here. And so the process is pretty straightforward. Like they count the frequency of each unique answer you have sampled, and the answer that appears the most often is considered the one with highest confidence. So this diagram just shows that this perfectly, like showing how multiple different reasoning passes can be sampled, and the most frequent final answer would be the most trusted one, right? And since you have multiple samples now, and you can calculate the more complicated ways, but other than just majority vote. So like I said, majority vote is simple, but it's relying on finding the exact matches, right? So sometimes you do not have the exact matches. You just, in the semantic meaning space, you have some variations on the word, but the semantic meaning is the same. But you can use some similarity metrics to judge whether they are belonging to the same clusters of semantic meanings or not. So you have different ways to calculate the similarity. And then another method just cut off the threshold, saying if it's smaller than this threshold, I'm thinking they are the same, and then using the majority vote to calculate their uncertainty, their confidence, right? Okay, so I think that basically concludes the confidence-based methods. Next section will be the applications of those uncertainty and confidence. Before that, I'll take questions here.
With the chart similarity, I could see doing that on a simple term, a concept that's like an embedding vector. But if you have a long paragraph that's talking about
yeah, you're right.
that would be very
Yeah, you're right. So that's the reason why later people are using like entailment or the complex method models. Get that.
With the self-evaluation of the confidence, have you noticed that it depends on the type of data set that you're performing the confidence?
Yes, you're right. That P2 is definitely very like the performance change dramatically if you are applying to different data sets.
Yeah. In the sense that I've seen with like if the task is more challenging, I find that model tends to be very confident most of the time.
Yeah, so also if the model is bigger, it's performing better. It's sort of providing the idea like whether they can generalize to the out of distribution samples or not. Yeah. Okay, then let's move on to the applications. So after we quantify the uncertainty, what we usually want is it's two directions, right? So you want for better language models, or you want for your domain tasks. And the first direction, like I said, is for better LLMs. So you can use that think about uncertainty quantification as a test time scaling procedure. It can improve your test time accuracy or efficiency. So this method those two methods are speculative rejection and best of n. So some works explore the ways to prune the tokens during the reasoning or generation process. They could train an intermediate model, use it for scoring the generation quality, and the left-hand side is the speculative rejection, which use a reward model in the middle to estimate the partial generation quality. So it early stops if the sampled sequence it has lower scores and stands for the low quality. You can use uncertainty, sampling multiple times, or uncertainty or entropy as a additional reward model as well. So on the right-hand side, this self-truncation best of n method evaluates the latent embedding of the early generation. So the latent embedding of each thinking path will be used to calculate the pairwise consistency between other tokens. And like you could think of that signal of uncertainty. And the sequence with the highest consistency are more likely to arrive the final correct answer. And another method is tree of, like, more specific way of uncertainty is a tree of uncertain thoughts. So in this paper, they are saying like the tree of thoughts method, they're directly improving on tree of thoughts methods. And they are saying that tree of thoughts methods overlooks the model's local uncertainty at each intermediate thought step. So they can lead to this brittle or overconfidence in the final decisions. So to address this issue, they introduce this uncertainty on when they generate new nodes. They sample multiple candidates for each node and using Monte Carlo dropouts and compute the variance of their evaluation scores as a local uncertainty metric. So then this uncertainty metric is then combined with the standard values, and then they are using this term called UQ VU ranking. So it's value divided by the uncertainty. If it's high uncertainty, you can think of this value, this VU ranking is lower, so that it can be used in either depth first or breadth first search, and favoring the passes that have both high value and low uncertainty if you're using this V divided by U matrix here. And like I said, if you're using breadth first search on the right-hand side, the key thing here is basically you're selecting the top B states at each step based on the value to uncertainty ratio. And then this sort of promoting the confident exploration over diverse passes. If you're using depth first search, on the other hand, then you are continuing the search or continuing expanding only when certain value exceeds a threshold and the consistency remains low. So this is additional term here. And these are the results. So overall, you can see that the tree of uncertain thoughts, they show that rejecting a local uncertainty signal into tree-based reasoning can boost their performance. And there are two kind of experiment settings. One is the mini crossworlds, and the other one is the game of 24. So mini crossworlds has three levels of success. If they are having accuracy, they are having letters accurate, or they're having the words accurate, or they're having the whole answer or the whole game accurate. They are validating three levels of success rate. And you can see that the tree of uncertain thoughts is performing better. This line is performing better than the other one. But even though it's it's a little bit marginal, but it's still improving because this game is still considered as a hard one. And then the game of 24 is also, and in this way, they're evaluating how much of the Monte Carlo, how many of the Monte Carlo sampling they need to do. Usually 20 is enough. You can see after 20 is getting some plateau on the improve or the success rate. And then another direction of improving the better long-term models is to incorporate it into your training process. There's no longer test time, is probably using your training. So this one is showing that, okay, humans, they can improve, you can provide, if you ask human labelers to label their uncertainty on the preference, human can do that, even though it's a little bit hard. But for AI, it's really hard. The current preference data we use is either I prefer this one over that one. That's either 1 or 0, right? But humans' preference should have certain uncertainty, right? So I'm maybe 60% prefer this one because of I'm not sure, and how to incorporate that uncertainty into your longer model is what this paper is doing. So instead of just using one preference of like 0 and 1 preference data, they're assigning each preference data a confidence score or the uncertainty score, trying to change the preference data from 0 to 1 into a scale between 0 and 1. And then they're comparing this method with existing uncertainty based preference data with supervised fine tuning and or they are using PPO-based method or DPO-based method, you can see that they're showing consistent improvements. And there another way of doing language model training. You can just directly change your reward signal if you're using reward-based model to train your language model. In the reasoning tasks specifically, people are using this reward. It's called a verification reward. If they are successfully get to the final answer, then this has a 1. If it's not, it's a 0. It's a very sparse reward. And it's either 0 and 1s. But this method here is called RLCR. It's using the confidence as a reward, internal reward, and it's no longer 0 and 1s. They are having buyer scores. Like I said before, you can use buyer score. You can also use the other confidence measures as well to integrate into your reward signal, turn that into a non-binary labels with from a non-binary labels to a scalar value, and then their methods show that this RLCR is having much better performance than the others with soft fine-tuning, supervised fine-tuning. All right, so that's it for the category on using uncertainty quantification for a better LMs. Either you can use it for test time or training time. And then the second category would be certain specific applications. One specific application we see in the training right now is to do robotics tasks. And so it's people in robotics are acknowledging that language models show remarkable performance at zero-shot task planners for robotic manipulation. But they do suffer a hallucination problem, like we said before. So in this diagram, if a robot is told to open open the drawer, and then they use language models as a planner. So they're generating detailed sub-goals that they want this robot to achieve. So after executing each sub-goal, then there is a failure detector to decide whether there's a failure on the sub-goal, instead of traditionally they are just evaluated based on the final execution on the evaluation on whether they are successfully open the drawer or not. So now they are detailing the failure detection into certain sub-goals, and this failure detector is uncertainty based. So they are using different kind of uncertainty quantification-based methods like token probability, entropy, and self-evaluate confidence to measure whether this failure is actually a failure or not. And then with this simple idea, and then they're saying, okay, if this one is very high, having a high uncertainty, then they are going to involve human to judge, help them judge, to do early stopping and to have human to judge whether this has a correct estimation or not for a failure, right? And with this simple strategy, they have a higher success rate than the traditional ones without this exploitation on the specific steps. Another, you can think of they are involving humans in the loop very actively if your threshold is not cutting well, right? But people also are acknowledging that if you need to, the subtasks, if you're directly putting the description of the image and the description of the subtask into the language model, it gives you certain uncertainty, but it's not grounded in the input as well. So this is the reason why people are doing this kind of task. So when the user asks, can you get the coffee cup from the living room? So the robots first ground its perception in the scene. So if there's only a cup, a mug, a cat, a table, and a couch in the image. If it's not having any like a mug or cup in the image, the subtask will not be executed, even though it's generated by the language model, right? So just having additional layer trying to ground the probabilities with the actual the scenes. So the whole step is like this. So the system is called the leap. They firstly have the prompts to generate the subtasks as before. And then they are having a second step is called scene grounding. So if there is a plastic ball, they're asking like if the plastic ball is in the scene or not. And every step will be happening, will be assigned a vector, right? So here you have 4 sub goals or 4 sub steps candidate step you can choose from. And for each sub candidate you can choose from, you will be assigned with a 1 or 0 or probability in this vector, right? If it's appeared in the scene or not, the probability of it being in the scene. And then they're using language models to estimate the uncertainty as well. So the prompt is like if there is something in a plastic ball, and then the task is put metal ball in the microwave, and then they are saying, is this possible and safe to incorporate this word knowledge into it? And then the language model will generate with this estimation, with this self-evaluation, and then they will reject all the possible candidates with certain lower threshold, and this combine this vector, this uncertainty or confidence estimation with the previous grounded scene vector. And if they will only ask for humans' help if it's larger than a threshold and it's possible and it's happening in the scene, right? So if it's not happening in the scene, like it's not say here, this landfill bin is not found in the context, then this one will be not compared, even though it has high uncertainty here. And then this one will be the first metal bowl is appeared in the scene, and then they have an uncertainty here, and then they will cut a threshold on the final prediction set. And if it's larger than a certain threshold, they will ask for humans' input. So you can see here in this step is cutting out a lot of the candidates, and then the humans are not much bothered by the asking for to get the robots to complete the task. And then in this is their results. So their prompts are having like the prompt here is just prompt LM to output the prediction set. And then these the binary method is just prompt the LM to output a binary indicator. So in both settings here, and their method in green line is achieving the best performance, and right-hand side bot is just a figure showing that its average prediction size. So the final prediction size is pretty small. It's only 2 usually. Basically, they're saying they're really asking for humans' help that remains ambiguous. And another application, I would just quickly scan this. We see people are using uncertainty quantification in sim-to-real transfer for the control of traffic signals. And we also see that people are doing where people are doing clinical predictions in healthcare, they're also using the uncertainty quantification, but they're using very simple ones, either entropy or the verbalized self-evaluation uncertainty quantification method. So in the end, I will quickly go through, I think we are running out of time, and I will just quickly go through some open challenges. The first problem that I'm we discussed in the previous Q&A is the evaluation for uncertainty quantification is pretty sensitive. So all the previous methods we talked about before, AUROC and the calibration error, we're doing the binary or the yes and no, whether it's correct or not, just justification. But for open-ended tasks, you are relying on some external model to judge whether this answer is fitting with your golden answer, right? So if your golden, so here, this is a general step of evaluation. You have existing method, you have a long-winded model, you generate multiple times, then you calculate their confidence, you get the confidence score, and this you are comparing the correctness, whether this generated answer is correct or not. You're having this function here, but this function actually, usually they will have a cutting threshold. If it's the similarities between the generated answer and the golden answer is larger than the threshold, they will think as 1. Otherwise, they're considered as 0. But you can think, you can see in this figure, the x-axis is the changing of this threshold. If it's the lines are different uncertainty quantification methods. If the threshold changes, the performance of your the ranking of your uncertainty quantification methods also changes. So it's very sensitive to the threshold you're deciding on whether it's correct or not. And so especially even though the threshold is very high, it's still like a lot of methods are dropping. Right? And in this work, they're saying, okay, how about we just free us from this judge on whether these two answers are correct or not. They're just transforming this judgment into a multi-choice problem. Every answer will be considered as a choice here. And they are just doing the correctness justification on the logics, on the probabilities now. Okay. And then another drawbacks people always criticizing on the uncertainty quantification method is that multiple generation uncertainty quantification method usually cost more tokens or more queries, and but they are having marginal gains. In this paper, this is a paper like I personally like that's doing a lot of benchmarking evaluations. They're finding out like a lot of the methods, they are not, they're having marginal gains on the reliability on the AUROC. And a single generation consistency matches or performs than the multiple rounds of generation. So maybe it's a good choice to just using one single round with white box setting other than just black box setting, sample it multiple times. And this is also another experiment results. And this is a performance comparison of a single sample method and multi-sample method. So the x-axis is the performance of single sample performance, and the y-axis is the multiple rounds of generation. You can see if it's lower than the area, it means that the single round performance is better than the multiple rounds methods, uncertainty quantification method. You can think of like this area has a much more dots than the upper area, but also you can find out like under high AUROC performances, maybe these two methods are not really differentiable anymore. So that sort of indicates like the single sample methods is enough. Okay, then another open challenge for now, like we only introduced language models, but we also have a lot of multimodal language model as well. But for multimodal language models, it's hard to judge their input semantics, because for image, the semantics for the image is still an open challenge as well. If you have a language model or if you have a foundation model that understands the semantics, it's basically a good model for the language model as well. But right now, people are finding like current multimodal language models, they're still have very high, having higher uncertainty than the single language inputs models. So if you're input a language into the model, it will have lower uncertainty than you have the both image and the text input. This is what this paper had found. And then they propose that maybe we can do some perturbation on the image as well, not just perturbation on the language. We can perturbate on the image semantics, but I think it's very hard as well because the generation of images with semantic manipulation is still a challenging for image generation. Also, you can do some domain-specific fusion, and you can also think about this manipulation on the image as a joint optimization of adversarial training and cross-modal backdoor attacks. So this is the possible open directions for this if you want to quantify the cross-modality uncertainty. And the last one, I think, is the interpretability. Like I said before, traditional uncertainty quantification methods, we care about aleatoric and epistemic. The reason why we care about that is because that helps us to decide where we should focus on to improve our models, right? So if it's just model uncertainty, and if it's just data uncertainty, we can just focus on should we get more data or should we just propose a better model? So it's very hard now for the large language model uncertainty quantification methods to judge whether it's actually from the data or from the model. So I think it's still an open challenge. All right, so with that, that concludes this tutorial. And you can find the paper and website and the slides on the website as well. And I'm open to any questions if you have. Then if you do not, then that's it for this tutorial. Thank you for being here. Hey, questions?
This is just kind of a general question. I'm curious to hear your thoughts or if you've seen any work exploring confidence estimation or uncertainty quantification for problems where you have your model output is complex. So maybe you give a text input and you ask the model multiple questions about the text and it needs to answer all of them.
Oh,
something like that.
Just trying to understand your question. So you're saying the output is complex.
Yeah.
It could be the reasoning passes. Or
yeah, it might be like a complicated reasoning path, or it could be like you batch multiple questions.
Yeah, so previously we talked about one specific category of methods like uncertainty quantification for reasoning. So you can have another model help you to form a topology of your reasoning path, then just compare the topology. That's one way. And in the slides, I didn't talk about here, but in the slides on the website, we also have talk about like in the agentic systems, your outcome also influenced by the other like incoming text from the other agents is also a open challenge for the current uncertainty quantification method to quantify the agentic systems. So for the reasoning part, I have the answer in the slide, but for the agentic systems, I think it's still an open problem. Yeah.
Another question. During the, let's say, all of the application sections, we have the fast time optimizations. I think we can call it optimization. If you're selecting some of these paths against the other, how is the latency being considered in terms of this metrics? Like, do we have some comparison of method A, method B, and what is the cost of the latency?
No, I don't think there is a method right now comparing that, but that will be an interesting area because right now we previously there's some paper analyzing the redundancy of expanding the nodes, right? So if they have a redundancy expanding a node, then those kind of redundancy on the reasoning steps, they could be replaced by the estimation on each node for the uncertainty. So I think it's interesting to see that comparison as well.
Yeah, another thing is that if it's also related to some of these methods, based on energy, like energy-based methods, I think Lick also talks a lot about this. Because we are still also trying to follow the correct path while doing the response rate. So there's some similarity between these two.
Yeah, I think so. Yeah. Oh, I think this one first.
Yeah, so I find one of the application you showed that the idea is quite interesting for the robotics one. It's like ask for the plan, and if the confidence is low, it's like trying to kind of ask them how difficult you think the task would be.
Yeah.
And if they say low confident, then the chances of they can not do it is not high, right? Don't do it. So I'm just curious, in general, is there any way to ask it to assess, the confidence of solving particular problem?
I think this just Pichu, like self-evaluate. You can just ask them directly, or you can specify. I think for most of the tasks, you can just specify the context, like say that the hand, the manipulation, or it's just door fetching or just moving. Those kind of like task specification could be helpful for the language model to judge whether it is a hard task or easy task.
But for that, do they calibrate already with accuracy or?
No, they do not. They just do it directly. Yeah. Okay, so this one first.
Has there been work with some of the test time training, evaluating the certainty of some of those that might have been impacted by what you're using for test time training as far as how relevant your examples are for the upcoming question?
Yeah, so I think in this method, here, let me see. Is it here? I don't think they show it here. But I think in this paper, they did those kind of evaluation. What kind of uncertainty quantification method should be used or is better? But I feel like there's no, it's always like trade-offs, right? So when you are using a more multiple samplings has marginal improvements, but you don't know those marginal improvement well, how that will influence the post-training final performance. I think there is the gap between uncertainty and the direct relationship with final model performance. Yeah.
I had a question really just about what you kind of saw while you were doing the survey. So you're doing this large survey of all this literature. I saw most of the examples we went through in the slides were like related to like classification or answering like a simple question. Was there anybody kind of taking these methods and applying them to like building like knowledge graphs or identifying relationships between entities, like more complex?
I think one of the application we didn't put it here is actually like on the knowledge graph on the R. I think what we have seen RAG applications with uncertainty quantification methods. Yeah, so that's short answer. Yeah.
Okay, I guess the follow-up then is like, do you think is it worth it? Like you kind of at the end here, you were sort of talking about, I think, small gains to area under the curve for classification. I mean, how for practitioners, how much should we think about?
So I don't want to like change the message. Like I did not have the message say marginal improvements on compared to classification accuracy. I'm saying those different quantification methods, they could vary, and sometimes using more complex methods, just having a simple marginal improvement on the simple methods. But the uncertainty quantification method itself still a working method, but it's just that the variance of them is pretty small, right? If you're, in my personal belief, if you use uncertainty quantification, or traditionally in the traditional machine learning, if you use uncertainty quantification methods, it's generally better than just method without uncertainty quantification. Yeah. Okay. All right. If no more questions, then that's it for this tutorial. Thanks for being here.